All right. Happy Monday. Good morning. Good morning. Good morning. How are y'all doing? Hopefully everybody had a respectably wonderful or whatever. It doesn't have to be wonderful. My poor daughter is sick. I've gotten a few texts from some other people too where their kids are sick. So there's a bug going around right now. It's just a normal bug. They happen. But yeah. I'm so tired. It will be okay. No fun for anybody. Sorry, I am working out a couple of things. I am almost done. And let's get rolling. Okay, so we got a lot to get through, of course. You guys probably already know that. We have been, I think, learning pretty darn well. I had that take home assignment for y'all to do. And a lot of people did it. Most everybody did it. There were definitely people that didn't end up texting me, but that's kind of how life goes. Probably forgot. But I was asking everybody to send me those diagrams of a basically excitation contraction coupling process, and then throw in some um, sympathetic nervous system stuff. Know what I mean? Jelly beans. Everybody that sent me a picture, wow, great job. You guys really took it seriously, and I appreciate the heck out of that. That's what it's all about. That's exactly what we need. Is we need to be able to not only understand what is happening if the heart is just straight up beating, contracting, relaxing, but we got to think about how the body is going to try to increase cardiac output and decrease cardiac output. You can't just understand that the function of the heart is cardiac output. You got to understand that homeostasis happens. And if the body needs more blood, we got to figure out a way to get more blood. And if the body needs less blood, then we got to slow things down. So, everybody, cardiac output. What's the equation for cardiac output? What two variables can we change in order to change cardiac output? Beautiful, 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 beautiful. Heart rate times stroke volume. How does the body go about changing heart rate in normal everyday scenarios? What does the body use? I was like, what the heck is CISPAS? Yeah, you got it. You got it. Guys, I got to push forward, but it's the autonomic nervous system. In everyday normal scenarios, the autonomic nervous system, please write this down. It's the autonomic nervous system that regulates minute changes in cardiac output. If you stand up from your desk, you better increase cardiac output to be able to reach the blood supply demand of tissues. You got to increase blood pressures, you got to increase that heart rate, you got to increase the strength that that heart beats ever so slightly. It doesn't have to be large variables. It doesn't have to be 60 to 120, right? Going from 60 to 70, that requires the sympathetic nervous system in terms of heart rate. I hope that makes sense. Going from 60 to 62, that requires the sympathetic nervous system. It's not just magic. Going from 90 to 70, that requires turning that sympathetic nervous system off and turning the parasympathetic nervous system on. please, on a test, never just tell me that the parasympathetic nervous system turns on. That is not enough. You also must say that we turn the sympathetic nervous system off. Maybe that's something you haven't thought about before, but does that make sense? If the sympathetic nervous system is never turned off, then it still wins. And that's what something like coffee does, right? It bypasses turning the sympathetic nervous system off. Yeah, I mean, it's normally a seesaw, but can we bypass that seesaw? Sure we can, right? That's what we do in our everyday life. If you drink some tea, you drink some coffee, you drink some Coke. What I basically asked you guys to go home and draw is this flow chart, but I asked you guys to draw it in a diagrammatic form. Remember, my YouTube video does exactly that. And it's a really, 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 really important part of your guys' upcoming exam. So you cannot, please don't say, I'll do it later. Okay, don't put it off, don't put it off, don't put it off. Goodness gracious, where's my diagram? I thought I had one handy here. Ah. All right. So the idea behind this flow chart goes as follows. If we need to increase stroke volume, and stroke volume is defined by how strong that heart beats. The stronger the force of contraction, the more blood can potentially be ejected from the heart. Why did I say potentially? What else is required for blood to be able to be ejected from the heart? What has to happen during the relaxation of the heart? Yeah, perfect, Andy. I know it's Monday. You guys are tired. I'm gonna push you. Good try, Trish. It has to do with how the heart has to fill with blood. End of story. So for me, that whole diastole phase of the heart, relaxation, allowing blood to fill back those chambers of the heart, that's a really important step, because who cares how hard that heart will beat? If it's not filled with blood, can't have a stroke volume. And that all comes into play with this story I'm about ready to go into. But stroke volume, we know, is related to both how that heart refills with blood and then also how strong that heart contracts. And what do we know about the force of contraction? What is it proportional to? Go ahead, write it down, even though it's right here. And not just any calcium concentration, but the calcium concentration inside of that ICF, not inside of the sarcoplasmic reticulum, inside of the ICF itself. So if stroke volume is determined by the force of contraction, the force of contraction is determined by the amount of calcium inside the ICF, then we can also say that stroke volume is determined by calcium. Does that make sense? You guys see that tie? And that's exactly what the sympathetic nervous system does, is it's going to increase the amount of calcium inside that ICF. And it goes through the same flow chart that we learned for heart rate in terms of here. Now, instead of funny channels and T-type calcium channels, just ignore that part right there. I don't have time to draw all this out for you. It's in the YouTube videos and everything. But norepinephrine and epinephrine bind to a beta-1 adrenergic receptor. Beta-1 adrenergic receptor has a G stimulatory protein attached to it that now activates adenylate cyclase. Adenylate cyclase does a double hydrolysis step that turns ATP into cyclic AMP, and cyclic AMP turns on pKa. And if this happens inside of these myocardial cells, what that pKa goes and does is it drops some phosphate groups on some of the proteins. So for instance here, what if I had a little inorganic phosphate dumped off on my L-type calcium channel? An inorganic phosphate, an inorganic phosphate, an inorganic phosphate. If I throw inorganic phosphates on the L-type calcium channels, when the action potential is gone, the L-type calcium channels will stay open just a little bit longer, right? You guys study this? Does that make sense? And therefore, a little bit more calcium will enter this cell than it normally would have. So those ryanodine receptors are open just a little bit longer, and the intracellular calcium concentration is increased just a little bit. Where else does pKa drop off an inorganic phosphate? What other protein that's drawn here is phosphorylated by pKa during sympathetic activation? Crickets. Good. Great, Ash. You got it. It's this calcium pump right here. Remember, this calcium pump right here, that needs energy to run. And we can actually alter the pump rate. We can alter this pump rate. And that's done through a protein called phospholambdin. Okay, so we got phospholambdin. This will be, I think, really the first time that I've been able to teach you guys about this. Phospholambdin. I think it's B. Goodness gracious, I need to remember. L-A-M-B. Yeah, B-A-N. Lambin. Lambin. Such a weird word. Not lambdin. Lambin. So phospholambdin. Phospholambdin is an interesting protein. Now, stick with me on this. This is going to get confusing for half a tick. Phospholambdin normally slows down the calcium pump. Okay, in a normal situation, phospholambdin slows down the calcium pump. But what if we inhibited phospholambdin? What if we inhibit the inhibitor? What's going to happen to the calcium pump if we inhibit the inhibitor? It's going to speed that calcium pump up. Does that make sense? And that's exactly what pKa does when it throws a phosphate group onto phospholambdin. Sometimes putting energy into the system will inhibit it. And that's what happens in the sympathetic nervous system here, is if we inhibit phospholambdin, now the calcium pump works faster. Yes, no, maybe so? All right, and now the most challenging part for students is coming up here. We got to get rolling. The most challenging part now has to do with the ryanodine receptors. Because we got to remember that ryanodine receptors, these are the gates for calcium to leave the SR. And ryanodine receptors are calcium-sensitive calcium channels. So they're only open if calcium is entering the ICF faster than it's being transported back. Because if it's being transported back to where it needs to go faster, then that ICF concentration starts to drop and the RYRs will close. So L-type calcium channels are held open just a little bit longer when they get phosphorylated. And those RYRs will stay open just a little bit longer. But once these L-type calcium channels close, we no longer have calcium entering from the ECF. And that's going to start to allow these ryanodine receptors to close. So let's think of these calcium pumps if the RYRs are open, and let's think of these calcium pumps if the RYRs are closed. If the RYR is open, and this pump is moving faster, and I know we went through this last week, but it's a tough concept. If the RYRs are open, because the L-type calcium channels are open and the pump is moving faster. What's happening to the amount of calcium entering the SR? Increase, decrease, no change as the calcium pump moves faster. What happens to the amount of calcium? And so what's going to happen to that concentration gradient? As there's more calcium in here and it's getting moved out of the ICF faster, what's going to happen to the gradient? Nope, nope, nope. Don't second guess yourself, Tariq. Remember, the gradient is the difference between the two sides. So if there's more calcium being moved in here and there's more calcium entering from the outside, then we're moving more calcium into the SR. And the difference between the two sides, let's say, for instance, we started with 9 here in the ICF. We added 1 from the ECF. Well, now it's 10, but now we're moving that in here faster. So this number here is dropping, this number here is increasing. Well, shit, the difference between those two is getting a lot bigger, right? Remember, it's just a difference. So all we need to do is use tiny little subjective numbers. So if the number here is increasing and the number here is getting a little bit smaller, the difference between those two is getting bigger. Just use numbers, right? If we started with 5 and 5, this side gets bigger, it becomes 7, this side gets smaller, it gets 3. What just happened to the difference between those two sides? It got a lot bigger. It went from a concentration gradient of 0 to a concentration gradient of 4. Yes, no, maybe so? So if the pump's moving faster, then the concentration gradient gets bigger. And what do we know about the speed that things move? The gradient is bigger, then the slope is steeper. And if that slope is steeper, what can happen to the rate that things move as long as they're allowed to? So now calcium is going to rush out of these RYRs faster. As long as the ryanodine receptor is open, calcium rushes out faster, and therefore can bind to troponin at a faster rate and increase the force of contraction to a greater degree. Yes, no, maybe so? As long as ryanodine receptors are open. But eventually these L-type calcium channels will close. If there's no more action potential, the L-type calcium channels will eventually close. Calcium stops entering from the ECF. The RYRs will close. And now what? Now we're simply removing calcium from the ICF at a faster rate. RYRs are closed, so the calcium can't rush back out again. So what's going to happen to the concentration of calcium in the ICF? Yeah, now we're decreasing. And since the pumps are moving faster, that concentration in the ICF is dropping faster. Make sense? And therefore, calcium's leaving troponin, and therefore the muscle relaxes faster. It's a really important part for me. You will be tested on that. I guarantee you. Just because your heart rate is going up, and just because your heart is beating stronger, if it can't relax faster and refill with blood, then it's all for naught. All right. All right. All right. All right. All right. Went to that. Sure. The RYRs are closed step. I mean, the point is exactly this, Tariq. Again, cardiac output equals heart rate times stroke volume. But stroke volume is dependent on two major variables. Stroke volume is not just force of contraction, although that's what we've kind of emphasized. Force of contraction, therefore, that's all about calcium. Stroke volume, remember the other variable that we learned can change stroke volume is venous return. True story, you guys remember that term, venous return? Because what venous return's telling us is that more blood that enters the heart or less blood that enters the heart. So this is all about refilling. When you hear the word venous return, what we're really referring to is the refilling of the heart. It's called the preload. So stroke volume is not just dependent on how strong it beats, but it's also dependent on how much blood is in that heart. And in order for that heart to refill with blood faster, I hope it stands to reason that we need to remove calcium from the ICF faster. Yes, no, maybe so? We can't just get more calcium in, therefore force of contraction goes up. At the exact same time, we need to make sure calcium gets out faster, so when the signal does stop, that heart relaxes faster. That's the only way we can get our heart rate up to about 180. That's maximum. Maximum that you want it to get to on a healthy person. Did that help, Tariq? It was a different way of explaining it, but that's, really to the point of what I want. Yeah, well, we're on our way to blood pressure. We need to get there, Heather. We're going to be doing blood pressure today for sure. We're going to talk all about blood pressure, blood flow, learn some new formulas, and learn how the pump of the body is what helps determine blood pressure. It's not the only thing, but it's pretty darn important. So anyways, that's what's going on here. Now, phospholambda, there's that whole, phosphorylation of phospholambda actually causes an increase in the speed of that calcium pump. Don't forget ATPase. All pumps are ACEs. They're all enzymes that hydrolyze ATP, so that's why they call them ATPases. And it's running faster. Now, if the RYR is open, then calcium can be released faster. And that's why there's a more forceful, what the hell's going on here? Forceful contraction. But if that RYR closes, then calcium's removed from the cytosol faster, which now is going to reduce the amount of time that calcium's bound to troponin, and therefore that contraction is not only stronger, but it's shorter. So we're relaxing faster. All right. I love summaries. I love flowcharts. Even though you've seen this flowchart before, I hope it's starting to make more sense. What is our formula for cardiac output? Don't need to write it down. You've already done this. Cardiac output is equal to heart rate times stroke volume. Heart rate times stroke volume. Well, shit, there's your flow chart, right? Heart rate and stroke volume both affect cardiac output. Now, do we know that we can affect heart rate? Heck yeah, we know that we can. Parasympathetic activity decreases heart rate. Why is there not a red arrow over to stroke volume? Why does the parasympathetic nervous system not impact the stroke volume at all? Not directly. There are indirect controls, but no direct controls because there are no muscarinic receptors. There are no muscarinic receptors on blood vessels, and there's no muscarinic receptors on contractile myocardium. Great answer. Did that make sense to everybody? Sweet, sweet. Now, sympathetic activity does have an impact on blood vessels, and it does have an impact on contractile myocardial cells. And you guys learned how, right? Beta-1 adrenergic receptors on the contractile myocardium, alpha-1 adrenergic receptors on blood vessels causing vasoconstriction and venoconstriction, which causes more blood to return to the heart. And I asked you guys to write down a simple term last week. More blood in. What do we know? What's going to start happening? More blood into the heart, more blood out. Love it. Good. If we were in like a real class scenario, I'd be trying to act like a preacher right now, and I'd be like trying to get everybody to say that all together. Vasoconstriction, push blood faster. Venoconstriction is what we're dealing with here, not vasoconstriction. It is a type of vasoconstriction, but we're specifically acting on the inferior vena cava, Heather. Remember, I went through that, and those big longitudinal muscles that now shorten, and therefore more blood is dumped out of the storage system back into the heart. It's all about venous return here. Now, that being said, vasoconstriction, you got to imagine that we have during, fight or flight, part of your body is vasoconstricting and part of the body is vasodilating. So if all of the blood vessels to your digestive system vasoconstrict, the blood's got to go somewhere. It's not getting down to your digestive system, so it's going to quickly return to your heart. And then during that next heartbeat, with blood pressure being higher and whatnot during, sympathetic activity, it's going to get pushed out faster to the organs that need it. Did that make sense? Because there's more blood volume returning to the heart during that time. It's just not going out to those particular organs. All right, we'll come back to this whole ejection fraction thing. And then here's just another flow chart. Same idea, a little bit more thorough. You guys should use, let me give you a hint about Dr. H. This is how I write my increase, decrease, no change questions. I go into flow charts and I say, okay, I'm going to write a question about, right here. I'm going to change this variable. Or I'm going to go in, I'm going to change this variable. Or I'm going to go in, I'm going to change this variable. And that's where I write my increase, decrease, no change questions. Real simple. What would happen to the human body if we changed end diastolic volume? So you guys can go in and do the exact same thing using these flow charts. As you study, don't just learn the flow chart, break it. What would happen if we increase the force of contraction? Well, how can we increase the force of contraction? Calcium, calcium, calcium. Does that make sense? So I ask you guys, I plead with you guys, please don't just write these flow charts out, but think about each step. Think about how the parasympathetic nervous system decreases the heart rate. Well, acetylcholine has to bind the muscarinic receptors, which are GPCRs, which now hyperpolarize the cell because it opens up a transient potassium channel, and it slows down the rate of depolarization because it closes the funny channel for a short period of time. It decreases the pore size for the funny channel and the T-type calcium channel, therefore decreasing that heart rate. And can we impact that? Heck yeah, we can. There are drugs like atropine out there. Atropine is a muscarinic receptor blocker. So if I blocked muscarinic receptors on the heart, can I decrease that heart rate? Yes or no? If I block the muscarinic receptors, can I decrease that heart rate? No. No is the answer, right? Parasympathetic nervous system is no longer functional on the heart if I put in a specific muscarinic channel blocker. But what is still functioning? The sympathetic nervous system. Therefore, what's going to happen to that patient's heart rate? Increase, decrease, no change if you give them atropine. And one of the most clinically relevant heart boosters out there. Atropine's given all the dang time. Is this helpful? Does this make sense? Remember, on a test, here's my deal to y'all. I will always, you guys can see I'm pretty thorough in lecture. Like, I talk to you guys about all these specific keywords. Now, on a test, it's the keywords you're looking for. Because if I throw a brand new drug or a brand new toxin at you, don't focus on that. Don't focus on that toxin name and go, Dr. H never talked about this. That's not the point of the question, right? The point of the question will be, hey, here's a toxin, and it acts on this part of the heart. What sort of downstream effects would you expect? That's what you're trying to focus on. Look at the key word. What's being impacted? I promise I taught you about it. I promise some part of my lecture has covered that material. Okay, fair enough? Nothing will be brand new, but it does require critical thinking skills to work through. Find the key words. Okay. We have one lecture that we've basically skipped here. EKGs are today's lab. So we're going to kind of fit in some lecture lab. Open Skeskami. And EKGs can be a lot of fun, and they're kind of summarizing. Let me go, because I want to rewrite everything. Let me go back to this particular slide right here that we opened up one of our lectures, I think Wednesday's lecture last week, using. This was a really good summary slide where we said cardiac output equals heart rate times stroke volume. We know the heart rate is determined by autorhythmic cells, and we know stroke volume is determined by the contractile myocardial cells. The autorhythmic cells act because they are self-creating action potentials. Exactly, because their membranes are leaky. We know the primary autorhythmic cell, the natural pacemaker cell in the human body, is the SA node. And when it creates an action potential, that action potential can now travel through the heart. Please don't forget that as it travels through the heart, what's going to be happening to the tissues behind it? Is it still, does these, like, if I'm down in the AV node and the bundle of His, does the SA node still have an action potential? No. The answer is no, because the light switch gets turned on and it gets turned off. Does that make sense? This current is moving. It's moving from here through here to here. And as it does, the tissues behind it are repolarizing. Yes, no, maybe so? Cool. When these currents hit the contractile myocardial cells, that's when this depolarizing step occurs. What makes the contractile myocardial cells unique from the conducting system and from the autorhythmic cells is they have these L-type calcium channels, these big-ass bags of calcium and troponin, tropomyosin, actin, myosin, titin, nebulin, and therefore muscles can contract and relax. We end up with these big plateau phases. It's a beautiful thing. Current everywhere. This is current. 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 This is the movement of ions across the membrane. And that's the definition of current. Yes, no, maybe so? As long as we're moving ions across a resistor, we have current. I got a point here. Does everybody understand what I just said? As long as we're moving ions across the membrane, this is current. Not getting as much feedback today as I normally am. Probably just a Monday, little lagging, everybody. But that's okay. I'm still gonna kind of move on here. Almost everybody's heard of an EKG or an ECG, electrocardiogram. Why do we call it EKG? Because the guy that invented these, Eindhoven, he's Dutch. And in the Dutch language, cardio starts with a K. So EKG is what it all turned out as. I prefer to use the term EKG. My mentor for my cardiophysiology PhD was Dutch, so he was very adamant about EKGs. Like, stupid Americans. ECGs. What is an EKG? An EKG is a measurement of current. Can you please write that down? That's where my segue came into play back here, right? When we're looking at these action potentials, we're looking at currents. When we're looking at the conduction system of the heart, we're looking at currents. We're looking at the movement of ions. A very important note right off the bat, an EKG is not an action potential. I'll repeat, an EKG is not an action potential. An EKG is current. What do I mean exactly by that? If I'm looking at an autorhythmic cell here, and I'm seeing the movement of current, that means I'm seeing the movement of ions across this cell membrane. And these big rushes, both depolarizing and repolarizing, these big rushes of current, this is what an EKG will measure. This big depolarizing step here. An EKG can measure that. This big positive movement during the plateau phase, you're going to see an EKG isn't going to measure this very well because the current has both influx and efflux at the same time. This big step of potassium repolarization, that's current. It's a massive rush of ions across the cell membrane. Yes, they're moving out of the cell, but that's still current, right? True story? EKGs are probably going to be the #1 things you guys use clinically to monitor your patients' hearts. You should have a pretty basic understanding of an EKG. I'll end up coming back to this. This is anatomy, right? Anatomy is the study of structure, and every graph that you learned is anatomy. Graph is just this idea of structure, right? There's a y-axis, there's an x-axis. What does the actual line mean? What are the different parts of the line? That's just anatomy. It's not anatomy as you traditionally think it is, but it's still something we can learn pretty easy as anatomy. An EKG, for whatever reason, Einthoven started with the letter P and went up to the letter T. So every major landmark is just P, Q, R, S, T. P, Q, R, S, T. You'll see if you just draw a straight black line across, every demarcation from that line is given a letter. So the first big landmark is P. The second landmark deviated off of that flat line is Q, R, S. Next major deviation, T. P, Q, R, S, T. EKGs are pretty darn easy to label. And what do you guys learn that they are? Heather, I do not have an answer to that other than Einthoven wanted to make it simple but didn't want to use A, B, C, D, E. I literally don't have an answer to that. So what did I just say an EKG was? It's a measurement of current. Yes, awesome. Love it, love it, love it, love it, love it. Now, we are simply putting an electrode on our patient's skin. So it's not just any current, it's current that actually makes it to the body surface. And then these electrodes, these little pads that are very, very, very good at detecting electrical changes, these have wires on them. They lead off to a machine. That machine can actually now, basically write out these EKG graphs for us on a monitor. It's super cool. But these electrodes are placed in something called the Einthoven triangle. Okay, well, this is a 3-lead system. Nowadays, most places are using 12-lead systems, but you don't need to learn 12 leads here today. You'll learn that in your respective medical programs. If you're, going into dental, you probably won't have to learn about the 12-lead system. So lucky you, all the crazy vectors and stuff that occur in that 12-lead system. But a 3-lead system literally means there are 3 electrodes. There are 3 leads. This is the original Einthoven's triangle, where Einthoven put an electrode on the right wrist, the left wrist, and the left leg. And these electrodes could either be a negative charge, a positive charge, and that's it. I don't know why I kind of acted like there was another one. The electrodes could either monitor for negative charges or positive charges. So for instance, the right arm, you're going to put the negative electrode on. The right arm and the left leg, you're going to put a positive electrode and a ground on, respectively. All current moves towards a ground. So you'll notice here that there's an arrow. And on the right arm, there's a negative charge. And on that left ankle, there's a positive charge. Because on a ground, all current leads towards a ground. Yes, no, maybe so? You don't need you're not going to be tested on that. It's just a basic understanding of what you're reading. All current reads, you guys, not everybody has worked with electricity. You just got to trust me, and I don't want to go into the physics of grounds. But imagine a lightning bolt hitting a metal rod. That's in essence a grounding. All current's going to lead now through that rod down to the base of that rod. What do I call this? A ground? Is that what you're asking? Oh, this is Einthoven's triangle. Einthoven, E-I-N-T-H-O-V-E-N, Einthoven. I'm pretty sure that's how you spell his name. He's the guy that invented this, and it's just a triangle. All right, we're getting, I'm going, okay. You don't need to know this in that much detail, but you do want to understand these vectors. So right arm, negative charge, left arm, positive charge. All negative will move towards a positive charge. That's how electricity works. Negative moves towards a positive. So here in vector 1, there's going to be current running from the right arm to the left arm. Yes, no? And we can measure current as it's going in a positive direction. Lead 2 is from the right arm to the left leg. You guys are never going to have to replicate this for me. So you're not going to have to redraw this by any means. But current, it can be measured from a negative electrode to a positive electrode in this direction. Finally, left arm, if we're going to be running down lead 3, we're going to be getting a positive movement of charge that we can monitor going in this direction. Now we get these different vectors. AVR, that means a vector on the right, vector on the left, vector down towards the foot. That's what the F stands for, is towards the foot. So there's different vectors that we can monitor electricity on. Again, just bear with me. It's just the basic understanding of how an EKG works. So now, as electricity moves through the heart, depending on the direction that electrical current is moving, we're going to be able to see a different movement of vector current. What do I mean by that? I mean something like this. So right when the heart, well, let me go to a drawing we've already done. Let's go to a drawing like this. SA node fires. What did we say is going on with that current, that action potential? It's traveling through the atria first. True story? Do you guys see how it's going to be traveling in a direction that's slightly away from the SA node, slightly away from the SA node? So now if we were to look at this exact same picture, and now we think, hey, patient's got a right arm out here, patient's got a left arm out here, and patient's got a foot down here. And now we start putting in vectors, which are basically these arrows, right? We can say, depending on the direction that that current is moving, it's going to change what we see on an EKG. if the current's moving straight down this way, or if the current's moving back up this way, the current's moving in a different vector. Does that make sense? You don't have to overthink this. If the current's moving in a different direction, it's moving in a different vector. If the current's moving this way, it's a different vector. If the current's moving this way, it's a different vector. Yes, no, maybe so? And then if it's moving straight down, it's a different vector, so forth, so on. So it's not that complicated of an idea at first. It is a complicated idea. Don't get me wrong. EKGs are actually a lot more complex than we give them credit for sometimes. But yeah, I mean, if we're talking about current here, we're saying, hey, it's going dot, 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 it's going around, then it goes this way, then it shoots back out through the heart. It's going to be running on a different vector as it does this. Cool. I think that actually came out pretty well in the long run. That's exactly what's going on with an EKG here. Just don't write anything down with me. But we know that an SA node is where the action potential starts, and an action potential is current. So we're starting to measure current, boom, right there at the very beginning of that, well, heartbeat. Heart's not beating yet, but the first initial action potential has occurred. So do you think we can measure that current? Sure we can. And that's going to be the beginning of our EKG. Does that make sense? You guys with me? That I have current, therefore I have the, okay, cool. Sorry, there was a little bit of a lag. So since this, and so there's just two more ideas, and then I'm going to be flying through this. But look at this. This current is moving down and away, down and away. And what do we know? If we start up here towards the right arm and we're moving towards that left foot, what type of current did we say we're measuring? Positive current, right? It's moving towards this positive ground, true story? Or if it's moving towards the left arm, it's positive ground. Yes, no, maybe so? So the last part of this idea is exactly what I kind of started out with, that an EKG is not an action potential. This is not a measurement of depolarization and repolarization. Never think that. This is a measurement of current. So as long as current is moving towards a positive electrode, we're going to see a positive portion of this curve. And if it's moving towards a negative electrode, it's going to be coming back down. And if the currents balance out, if a current is moving towards both the positive and negative electrode at the same speed, then we're going to get a flat line. Does that make sense? It's just a measurement of current and the movement of current. Let me say that one more time. An EKG is not a measurement of an action potential, it's a measurement of current. If we have current moving towards a positive vector, we have a positive uptick in the curve. If it's moving towards a negative vector, it comes back down, and if those two vectors balance out, it's a flat line. Just because it's a flat line doesn't mean there is no current. That's not how it works. Just because it's a flat line, there's still current going through the heart during the PQRS T. Cool beans, Daddy-O? Daddy-O's? Okay, let's draw out an EKG. Let's draw out an EKG. I just find too many students say, well, boom, there we go. It's going up, it's going up, it's going up. Therefore, that's depolarization. No. This is not an action potential. So we'll come back to that idea. All right, EKGs are pretty easy to draw. You kind of want a lot of room. Make sure you give yourself a decent amount of room both to go up, go down, and do a couple of labels around it. And we're going to actually draw two EKGs across the board. So the way this works is basically you start at a relative flat line. I don't know whether that's flat or not. And now current's going to start to flow through the heart. So you're going to get a bump. Don't worry, we'll go back through and label all these things and have an understanding of what's going on. Now, current's still moving through the heart, but it's going to be both going towards the positive and negative vectors. So we're going to be able to get like a flattish line here. Then we're going to get a dip. Then we're going to get a skyrocket. Ah, my straight-ish line just died. Oh my gosh, that is horrible. What's wrong with me? Straight lines? No, thank you. This is typically going to come back down below this first demarcation. Comes back up. Flat line. A little bit longer of a flat line sometimes. Sometimes it's going to be shorter, but in a normal heart rhythm, we'll go ahead and write this. Now, big bump. This one tends to be a lot bigger than the first bump. Now a big, long, flat line. And then what's going to end up happening is this is one heartbeat. So where does the next heartbeat start? We're going to get to see another landmark that looks exactly like the very first one. You guys, when you go to study this, draw out, 2 or 3 EKGs on the same curve. It'll help you out quite a bit. All right, so how do we go and quickly label this? We just start to identify the deviations from flat. So the first place that deviates from flat is right here. So I'm just going to use a specific color. It doesn't matter which color, but right here, I'm going to put in kind of brackets here. There's my first change. We call this the P. Now, the P looks like a nice rounded wave. So physiologists call this the P wave. We're having a P wave. The next deviation from the flat line comes over here. Okay, it drops down. This dip down. This dip down. Well, P, what is this one going to be? It's going to be Q. Now, the Q is not a wave. We're going to kind of get into something that it gets combined with. We got Q. The next big one is this huge peak up here. This one up here, this peak. Everything above this point. All of this, everything up here is all called the R. And then this dip down here is going to be the S. These three things have, familiarity in their physiology. So they end up getting clustered together as something called a QRS complex. The last major demarcation from the curve, deviation from the curve, is this bigger wave over here. Well, I hope it stands to reason that this is T, and since it's a rounded wave, we're going to call it a T wave. And that's the basics of an EKG. There's a P wave, there's a QRS complex, and there's a T wave. So what's going on over here on the far right? What did I draw over here? The next P wave. The next P wave. And we kind of already did a little, understanding of what's going on right here. But if I were to try to think about this, remember, this is a measurement of current. So right here, when current starts to be measured, I hope it stands to reason that this is when the SA node fires an action potential. This is the very beginning of that action potential right there. Yes, no, maybe so? It's not this whole entire curve. Boom. This is the SA node action potential, literally that point right there. And then now that current is going to start to shoot out. It's going to shoot out through the heart. And it's going to be depolarizing those contractile myocardial tissues as it moves. Does that make sense? If I had a heart up here, we start here, and then it moves through what part of the heart first? What part of the heart is receiving all that current first? The atria. This is measuring the currents through the heart, exactly. Exactly. So what is going on here in this P wave right here? Well, this is your atria. All that atria, as it's depolarizing, as the current from the action potential is conducting itself through the atria, both the right atria and the left atria, it's depolarizing those contractile myocardial cells. And we can measure that atrial systole and atrial depolarization on this curve right here with the P wave. Okay, so we're going to end up writing each one of these things down. But I'm just going to get you guys started, is that P wave, I hope I gave myself enough room to do this. P wave is a representation of atrial depolarization. Notice how I did not say repolarization. All I'm saying is depolarization. Even though we're going up and back down again, this is still all depolarization. Why would it be able to come back down on a curve? Isn't down on a curve repolarization? I'm so confused right now. EKGs are a representation of electrical current and the direction that they're running on a vector. So don't think this is an action potential. This is not depolarization, repolarization. This is simply the direction the current is running. So if that current is moving towards a negative electrode, it comes back down or can drop down below if it's running towards a negative vector. That's all it's saying. Does that make sense? So that's why this is a representation of atrial depolarization. I drew this super duper duper small. Let's draw it a little bit bigger. Actually, let's do something a little bit more dramatic. I hate doing this. I don't know why. My brain just freaks out when I tear out any of my past notes. All right, so we're going super dramatic here, but that's okay. Because what do we know? What happens next? So far we've talked about SA node firing, and that's the very beginning of the EKG. And now we've talked about how that current moves through the internodal pathways as it runs out through the atria. So what happens next? What's going to happen to the current next? Where's it going? It's going to that AV node. And what do we know about the AV node? What is the importance of the AV node in this action potential conduction? What did we start writing down? Yeah, so good. Remember we called it the AV nodal delay. It has parasympathetic tone. So the parasympathetic nervous system is very active here. It likes to be active here. And it's going to slow current down. Yes, no, maybe so? I try to emphasize this where I said the current is going to get concentrated here. It's shooting through the atrium, and then it gets concentrated here. And it slows it down. Well, and if all that current is getting slowed down in the AV node, Are we going to be able to see it shooting out towards vectors? If it's all concentrated in the AV node, is it moving through the heart right now? Yes or no? No. So what are we going to see on an EKG? If there's no current that's shooting out towards vectors, we're going to see a flat line. Does that make sense? So this is the area from the end of the P wave. It starts right here, and it's going to go to the very beginning of that Q wave. This flat line right here, from the P to the Q, you guys can learn as the PQ. I'm okay with this. PQ segment is what it's called. It's also in a lot of textbooks, they're going to call it the PR. PR, and actually in your lab, it's called PR. And in some of my lectures, I've called it PR. I learned it as PR because that's how it was originally taught. But it's just this segment right here between the P and the very beginning of the Q. Okay, that little area right there is called the PQ, or we can actually say PR segment. And what did you guys just learn about part of the function of the PR segment? This is the AV nodal delay. So what would happen if the PQ segment was longer? Say, for instance, it took up more time. It was longer because this is x-axis is time, of course. What do we now know about that patient's heart rate? Is it speeding up or is it slowing down as that AV nodal delay gets longer? So it's a really simple thing to see on an EKG is you can look at that AV nodal delay and you could start to get an indication on how well that patient's parasympathetic nervous system's happening and working and the AV nodal delay. Now, the next thing to think about here is with our heart picture. If I'm delaying the signal right here, remember the current had just shot through contractile myocardial tissue in the atria, and that's what this action potential right here is. Depolarization of contractile myocardial tissue, that's the P wave. All of this depolarizing current, all of this massive increase as sodium rushes into the cell, that's this entire P wave. But when it makes it to the AV node, it slows everything down. What's going to be happening inside of the atria? What's going to be happening inside of the atria is the next part of the contractile myocardial action potential. Think about it in terms of timing. The action potential just shot through the atria. It just shot through the atria, and about 100 to 200 milliseconds later, it's sitting here in the plateau phase. Yes, no, maybe so? So as the AV node is delaying the current, the atria is actually contracting. Does that make sense? While the AV node is delaying the current, we got to think about what's happening behind it. That depolarizing current that had just rushed through the internodal pathways is now somewhere 200 milliseconds further along the line. So that's where the plateau phase for atria is occurring. So during the PQ segment, not only is it the AV nodal delay, but this is also a measurement of atrial systole. This is when the atria is contracting, right here, where there's a flat line. Because we have a plateau phase, and as long as we have a plateau phase, currents moving in and currents moving out, and they cancel. Does that make sense? Cool. Now, what happens next? The AV node is going to delay everything down, but where does it go next? Bundle of His. then down through bundle branches, which is part of the interventricular septum, and finally into the Purkinje fibers, which now shoots all this electrical signal back up through the heart. Massive amounts of current shooting through that heart, going up through that heart. Yeah? Yeah. Holy moly. So let's think about this. Right here at the end of the AV nodal delay, that's right where that bundle of His current is going to start moving this stuff down through the heart. So this Q is going to be the very, bundle of His, just a short little segment. And then Q, the rest of the Q is current going down through those bundle branches. And all that current moving through those bundle branches is going to eventually hit the Purkinje fibers. And we get these massive rushes of current as tons of electricity, tons of current is moving through the ventricular myocardium. All of this, Q, R, and S, is a measurement of this ventricular depolarization. And that's kind of where I want you guys to know QRS is ventricular depolarization. So what if somebody did have a complete bundle block? That would mean that their bundle of His is stopping current from moving through it. If I did a complete bundle block right there, you guys see how you might get a P wave, but what's going to happen to the QRS complex in that patient? We're blocking current from coming down here. You're going to lose the QRS. Does that make sense to everybody? You guys do not need to be able to tell me pretty much anything about abnormal EKGs. There are 1,000-page textbooks on EKGs. The textbooks, all the EKGs are insane. Let's just put it that way. Ultimately, it all depends on the patient. It all depends on where the electrodes are placed, and it all depends on the vector that you're looking at. In a 12-lead system, you're looking at basically 12 different vectors instead of a 3-lead system where you there's even more than 12 vectors in a 12-lead system, but it's insane. That's why it takes these specialized cardiologists to be able to really read an EKG. So just learn the basics here. Nursing programs, you guys are going to go off of these basics and you're going to learn a lot more about 12-lead systems. All right, next. All of this current has now made it down. We used an orange. All of this current has now shot down through the bundle of His, bundle branches as it's moving down, and at the end of the road down here, it went through the Purkinje fibers. So what happens next? Now that all of the ventricular myocardial tissue has depolarized, what can happen next? Remember, we've got an action potential. Just use the words with the diagram. We got ourselves an RMP, we got ourselves a threshold. We don't need to worry about this too much in terms of labeling and everything. I said, if I have a ventricular myocardial, that's the contractile myocardium, and now it's depolarized, well, that's not a straight line, whatever. What's going to happen next? Good, Beck. Does that make sense, everybody? We just depolarized, so what happens next? The plateau phase happens next. Yes, no, maybe so? There sure looks like there's a flat line right here to me. From this point to this point is a flat line, which means for some reason current's not really moving around, or at least we're not seeing it. Well, the reason we don't see it is because that is ventricular systole. So from the end of the S to the beginning of the T, this is called the ST segment. And the ST segment is ventricular systole. Don't let anything that you read trick you. Does ventricular systole potentially start a little bit more in the R and the S? Sure, there might be a little bit of contraction because some of those earlier ventricular myocardial tissue might start contracting up here. But when's the compilation of all of those ventricular myocardium going to be contracting, which is where the force comes to be able to push the blood out? It's coming during the ST segment, not the RS, not the QRS, nowhere in the QRS segment. Ventricular systole is occurring during that ST segment. So what happens next? Look at my little action potential curve. I just had the plateau phase. What happens next? Repolarization. Whoa, hold on though. What is happening right here during the repolarization phase? What ions do? Potassium, not influx. Better check yourself before you wreck yourself. I don't know why I said that. Yeah, that's potassium efflux, right? Efflux, efflux, efflux. The potassium's higher inside the cells, and that potassium rushes out. You guys remember how I kind of started all of this? The EKG is not a measurement of an action potential. It's a measurement of current. Is this current? And is the entire ventricular system repolarizing right now? This is definitely current. And this is definitely when all of this part, everything right here is repolarizing. It's a massive flood of potassium rushing out of all of those contractile myocardial cells pretty much at the exact same time. That's your T wave. T wave is ventricular repolarization. Yes, no, maybe so? What did you guys learn about contraction and relaxation? Contraction is due to the entry of calcium into that cell. So contraction starts as calcium starts to enter. So contraction starts, if I were to draw this on the same curve as my action potential, contraction is going to ramp up, ramp up, ramp up. When does contraction end? When the calcium is moved out. And calcium moving out of the cell is not immediate. It takes time for calcium to move out of that cell. So the relaxation phase occurs after repolarization. Does that make sense? This is contraction, this is relaxation. Relaxation is occurring after repolarization. Well, look what I got right here. Look at this big chunk of time between the end of the T wave and the beginning of the next P wave. There's no current moving through the heart. There's no action potential. So this is the time when those L-type calcium channels are closed. The ryanodine receptors are closed. And those contractile myocardial tissues are relaxing. Does that make sense? This goes from the end of the T I already used this color. It sure looks familiar. I feel like I end up using a lot of here. Pink. That one will stand out. This one here goes from the end of the T to the beginning of the next P. So this is TP, right? Anybody know Beavis and Butthead and Beavis, right? Need some TP for my bunghole. Yeah, I could say that. Bunghole is just a word for where they put the cork into the keg of beer. So it's not a bad term. So TP, TP from toilet paper, right? TP. And yeah, this is called the TP segment or TP interval. And this is the period of time. Yeah, seriously. This is the period of time as that heart is relaxing. Okay, the entire set of ventricles right now, they're relaxing. So TP, I just want to double check my wording that I have here for y'all. It's in a lab. Yeah, TP, but we'll come back to that. I just don't know whether I have TP segment or TP interval. It just depends on the textbook. So I'm going to write down segment, and it might be interval in your lab. I never remember which one it is. But that TP segment, this is ventricular. Very important that we write ventricular. It's not atrial diastole, it's ventricular diastole. This is when the ventricles are relaxing. The atria relaxed over here, but we lose the whole atrial relaxation, being able to see it, because the atria are relaxing as the ventricles are contracting. I mean, the ventricles are like 90+% of heart mass, you know, so yeah, you're not going to really be able to see atrial relaxation. Does that make sense? What if we measured from the beginning of this P wave to the beginning of this P wave? What might that be a measurement of? The PP, PP, or R to R. It wouldn't matter where we measured from. If we measured from the beginning of one to the beginning of the next one, yeah, it's kind of the same thing. Melissa, not necessarily one contraction, because the contraction is only occurring during this period of time. Does that make sense? It's one heartbeat is contraction and relaxation. But from the beginning of P to the beginning of the next P, that would be one heartbeat. So it's really easy to measure a patient's heart rate using an EKG, because it's just, you know, a measurement between these 2 points right here. If this was 1 second, then that patient's heart rate would be exactly 60 beats per minute. Does that make sense? All right. So this information that we just went through right here is for both lecture and lab. We're still going to use our time because that's what we do in our summer class. Our summer class is so fast-paced. There's nothing else that we can do, but this is for both lecture and lab. So in EKG, I love this diagram. Now that you guys have everything written down that we just did, just pay attention to the pics. This EKG here is a representation of what's happening with current through the heart. Where do we know all that current starts during one heartbeat? It occurs way up here. Oops, in the SA node. So that current is going to be moving through the atria. You can see it's on an exact figure 8 like I drew. There are actually different parts of the internodal pathways, but you don't need to know all about them for this particular class. And as that current moves through the atria, it's depolarizing that atria. So the P wave is atrial depolarization. Now, depolarization, it takes, you know, 150 milliseconds-ish. It's pretty fast. But after atrial depolarization, that's when that plateau phase is occurring. Yes, no, maybe so? So after the atria is depolarized, that's when the atria are contracting. And you can see that in this picture, that the blue atria are looking like they're smushed down, right? And that's because the atria are contracting during the PR segment, but this is what I meant by PR, even though it's going from P to Q, it's just confusing the terminology that's used on it. Yes, yep, exactly. So this is where atrial systole is occurring. And then in addition, of course, all of that current is being held up by the AV node. So that green portion of this curve is the AV nodal delay. Same thing we just wrote down. So I hope this is just good redundancy. Now the current starts to shoot through that bundle of His, goes down through those bundle branches, ends up out in the Purkinje fibers, and that's that QRS complex. All of that is as the ventricles depolarize. But just like we talked about the atria, contraction doesn't come until after depolarization. So that area after ventricular depolarization is the ST segment. So that ST segment is now going to be a great representation of ventricular systole. The T wave, after the plateau phase, comes this massive rush of potassium out of the cells. This is repolarization. As those cells repolarize, there is a very large movement of potassium out of the cells. It's a big area. There's a lot of muscle mass. Therefore, there's lots of potassium, and that's why the T wave is so darn big. TP, they did use interval in this particular picture. We wrote segment in our little write down over here. So that we wrote TP segment, and in this picture, they said TP interval. Again, it just depends on the textbook that you're looking at. There are a difference between segments and intervals, but I'll deal with that later. Now, the TP interval, that's ventricular diastole. And of course, this is when the heart is relaxing, and this is when it's refilling with blood. TP interval, TP segment, definitely one that is an important one for you guys to know. So sort of the questions that I can ask are, you know, what is the area under the curve that is a representation of all of ventricular depolarization, for instance? So what's that answer going to be? QRS complex. Now, what if I said all current through the ventricles? That one's tricky. If I said all current through the ventricles, all current. So in other words, a representation of the entire contractile myocardial. Good try. You guys both came up with the same answer, both just slightly wrong. Remember, if it goes all the way, there's no current going right here. From TP, there's absolutely no current. This is not repolarization. This is when everything's just chilled out. So it's from Q to the end of T. It's from Q to the end of T. P is atria. The PQ is atria. So everything, the blue and the green here at the beginning, that's atrial current. Q all the way to the end of T, that's ventricular current. Does that make sense? So those are the sorts of questions that I can ask on both lecture and lab. If you kind of just understand and be able to differentiate atria versus ventricles versus relax, then that'll help you out quite a bit. Well, just one last representation of the same thing here. It's a little tricky, but it's crazy useful. And I love to remind you guys that medicine, we want to stay as non-invasive as possible and learn as much as we possibly can. And that's why something like a patient's blood pressure can tell us so much. I'll be teaching you more about blood pressure, but blood pressure is one of the greatest non-invasive ways to tell whether a patient is healthy or not. EKGs, totally non-invasive, just a couple of electrodes, and we can tell a ton about a patient's heart. Because if any one of these parts of the EKG are abnormal, then we can hone right in on what is a potential cause or what is a potential reason for that abnormality. It's a beautiful way to be able to look at a heart. Taking somebody's urine. Who here has been to the doctor's office and had to pee in a cup for any reason whatsoever? One of the most powerful non-invasive techniques known to mankind. Super non-invasive, although some people feel like their, privacy is invaded. It is what it is. And you can learn a lot from urine because urine comes from kidneys and kidneys are filtering your blood. So what's happening in your body will be happening in your urine. So you can see this right here, EKG, is one of the 3 most powerful non-invasive techniques. Blood draw are not completely non-invasive. We want to try to avoid blood draws as long as we can because patients have such an adverse effects to needles. Why would the EKG show no current? I mean, great question. What do we know about systole? Is that's where the plateau phase is happening, right, Heather? And anybody else that had that same question or it didn't hear me answer it earlier? If we have a plateau phase, then calcium's entering at pretty much the exact same rate that potassium's leaving. So positive entering, positive leaving, what's going to happen to current is it's going to balance out. Yes, no, maybe so? So they just subtract from one another. If you have 10 going in and 10 going out, then the machine's going to measure 0. Does that make sense, Heather? Cool. Awesome, guys. Again, this is both lab and lecture at the same time. So if we go to the lab material here, and then we're going to take a break and we'll come back. We go to the lab material here, labs for Unit 2. The last one you guys have to work with is EKGs. You have yourself your lab report. You can actually, I think this one right here, you can see it says COVID only. I don't know what's going on. Oh, online, not only. And then you can see that the handout is slightly different because you aren't going to be able to measure yourself. There is an EKG lab that you can click on and you can watch. I don't really find it all that useful, but it is available for you. And then you can actually go to a course tool. It's still the practical clinical skills. I hope you guys can still use it. Let me just double check here. Because it did not work for the blood pressure guy at all. That was sad. I kept on having the same problem everybody else did. But this is exactly what you can do now. You can go in, ventricular heart rate quiz, and what you can do, you see these blue lines over here, y'all? You can move them. And so what I want you guys to be thinking about is the EKG we just learned. Yes, it looks a little bit different because this is real. But can you guys still see the same landmarks? What's this at the tip of my arrow? What is that going to be right there? That's the P wave. What is this area right here that I'm circling? That's the QRS. You can notice there's something a little bit abnormal right here, but that's probably just a part of the the leads, like I was saying, right? If you put on electrodes on a different person, different people have different heart positions. Their hearts are actually positioned in the chest cavity slightly different. And as current runs down vectors in a different angle, it causes deviations to a normal EKG. It's a real pain. But this entire area right here, what might this all be? Even though it doesn't look exactly the same as what you guys just drew. Yeah, that's all the T wave. And then, of course, from here. So you can actually go in and move your calipers, and you can measure, you know, there's 100 milliseconds. That's how fast this is all happening. You can measure from the top of one R to the top of the next R. So this heart rate, one beat is in 0.79 seconds. So now you can actually do some dimensional analysis, and you can measure their heart rate. You guys need help with dimensional analysis, watch some of my videos. So yeah, that's up and working for you guys, which is awesome. And then you're going to be able to go in and measure some subjects using that exact method. So you're going to be measuring the R to R interval. Isn't that what I just did with that patient that I was just looking at? Where the heck is it? Right? There's an R to R. So you're going to write down that R to R interval. Make sense? And just read through the directions. It shouldn't take too much time. It shouldn't be too crazy. The PR interval, well, again, you're just going to go in here and you're going to find a end of 1P, and you're going to go to the R. You'll see this in your lab, but you'll be able to measure these different intervals. And that's all you're doing. PR interval, PR segment, QT interval, TP interval. These are all in this picture right here. So like the PR interval, QT interval, if you're going, Dr. H, you didn't teach us those, they're right here, okay? So it shows you everything that you need to know. You also have the lab report, the blank one. You guys know how this works, I think, at this point. This is the one you guys work on as a group. True story? Not too crazy hard. First part, draw a flow chart of the conduction system. So begin with the SA node, end with the myocardium. Second question. This is something we're going to do today. I'm going to teach you how to draw flowcharts representing the pressure gradients between the left atrium and left ventricle. So we're still going to work on this together. Use the EKG recording below and label the following. We just did this. There are some extra intervals in here that you can label as well. Again, what is a PR interval and a QT interval, that's all in your lab handout. During which part of the EKG does each event occur? Atrial depolarization, plateau stage of the atriomyocardial cells, which is the same thing as atrial systole. Ventricular depolarization, plateau stage of ventricular myocardial cells. Yeah, I'm fairly certain this is what we just did. Yes, no? I always try to give you guys the answers in a roundabout way. Normal range of time for PR and QT. Look these up online, all right? They're also in your lab handout, but you can look them up online. And therefore, if you go to look at a patient, you look at their PR interval, do they have a normal range? Is there a normal homeostatic value that we should be looking for? Of course, the answer is yes. And if it's outside of that normal homeostatic range, then we start to ask ourselves what's going on. The very last question on here is fill in this chart summarizing the ion changes that occur during a pacemaker potential. So this just takes you back to the pacemaker potential one more time. Sodium, calcium, calcium, potassium. Sodium, calcium, calcium, potassium. Sodium, you guys know what I'm talking about? And whether it's depolarizing, repolarization, influx or efflux, easy peasy, lemon squeezy. This particular lab tends to be the one that lab groups, I shouldn't jinx you guys, but it should be a 10 out of 10. It should be a pretty easy 10 out of 10 for y'all. EKG lab report. Oh yeah, that's right. I think I actually made a quiz for it, so I'll get this all worked out. I think during the spring, all I did was I had them actually, upload their own PDFs to the assignment rather than do the assignment like with a quiz. But I wrote up a quiz and I don't remember where the heck it's at, so I'll find that for y'all. There are just so many diagrams in the EKG lab report that I might end up just having you guys literally take pictures of your lab reports. So have one person per group with this lab report right here. Just take pictures of your answers and then upload it as a PDF. I'll keep you posted. That's probably the best way, honestly. It's super easy for me to grade it that way because there's so many graphs and flowcharts. It's always due next lab, so it'll be due Wednesday. All our lab reports are always due next lab. All right, you guys rock. You guys are so patient with me. I really appreciate that. I'm trying to get you guys through all the material. So different in an online format because I'm looking for feedback. I want the interaction with y'all, but that kind of slows things down a little bit. But let's go ahead and take a decent break. Let's come back at 50. We'll come back at 55 after. We are done basically with lab, but we need to finish the heart and start some blood flow stuff. So come back with your brains on, go get some coffee, go get some food, come back at 55 after. All right. We're back. Another like a little poltergeist reference to get you guys creeped out. All right. Not everybody gets the poltergeist reference anymore either. All my references are old. It's almost like I'm old. I don't know. It's weird. I feel young, but apparently I'm not. I don't know. We don't have much left to go through for the heart. That being said, I want to make sure to reemphasize how important the heart is for the human body. So almost everything we do from here on out is going to refer back to the heart. Respiratory system. Yes, it's about gas exchange, but the gas exchange is oxygen, carbon dioxide, and the whole point of gas exchange is to get that gas into the blood and get it transported out to the rest of the body. Does that make sense? Digestive system. Eat food, great. Digest food, great. No, that's not it. We need to get those nutrients and those vitamins, we need to get them into your bloodstream and transported to where they need to go. Renal system. Function of the renal system is to filter blood. All of this is going to be relying on blood movement, and blood movement relies on your heart, amongst some other things. But one of the major factors is your heart. So don't forget this material we're learning this unit. It will be reused and reused and reused. Is that clear? Cool. I don't know why I went into lab. We need lecture, unit 2. Still quite a bit left to get through here, like I kind of referring to, but I want to make sure you guys have that really strong background to be able to do what you need to do, again, for the rest of the semester. So the last thing that we're going to look at is this crazy mess of crazy. Yes, I said crazy twice in one sentence. That's how crazy it is. This is something called the Wiggers diagram, Wiggers. It was the name of the guy that invented it. So what he did was he said cardiophysiology is pretty confusing. There's lots of things going on. We know that one thing leads to the next, leads to the next, leads to the next. And that's kind of how I've been teaching you, right? Where SA node and understanding about action potential of an autorhythmic cell moving through the conduction pathway leads to an action potential in a contractile myocardial cell, which leads to contraction. And then when we lose that action potential, we lose the contraction, we start to relax. It's a story. Chapter 1 to chapter 2 to chapter 3 to chapter 4. So how do we get that entire story in Cliff Notes? And that's what the Wiggers diagram is, okay? This is your Cliff Notes right here. But you got to understand everything to this point to be able to put this all together. The major thing that you guys can refer to is right up here at top. The events of a cardiac cycle. There's that P wave, QRS, T wave, and then the TP over here, right? And we just walked through this earlier today. P wave is where atrial contraction is occurring. And atrial contraction can only occur if atrial depolarization is occurring, because that's what's going to allow that atrial plateau phase to be reached. So the PQ segment is where we have the AV nodal delay, but the atria are contracting. So now if we come down to this picture, you'll see it's color coordinated. That the green here matches up with the green here. The blue there, whatever the hell color that is there. I'm not good with colors. Peach? I don't know. Goes there, and then purple, but I know it's some form of, I don't know, I suck at colors. That goes there. You guys get the point, right? This is all color coordinated. You there? Am I there? Have I been talking? Whew, whew, scared me. I thought I was like a little bit of lag. Okay, so atrial contraction. Let's think about this in terms of ventricular diastole real quick. All of this purple out here, what is happening as the ventricles relax? What's happening as the ventricles relax? What's happening during ventricular diastole that's so damn important? Good. The heart's filling with blood. So during this period of time right here, during all of this purple, the heart's refilling with blood, refilling with blood, refilling with blood, and then an autorhythmic cell is going to spontaneously fire and start setting an action potential through the atria, at which point the blood that was kind of here inside of the atria, there's definitely some passive refilling of blood in those atria. Those atria are going to contract, because that's what's going on in that green phase right there, right? Those atria contract, and the blood that was passively filling up within those atria, it's going to eject down into the ventricles. So the last little blood that was inside the atria gets pushed down into the ventricles, at which point the ventricles have not only been passively refilling, but now we get this little splurge of extra blood. And this is the very end of diastole. Remember how we were talking about a volume of blood inside of the heart at the very end of diastole? And we said that is where the maximum volume of blood is going to be. Do you guys remember that from last week? It was pretty short, but maybe memorable. Maybe memorable, because I talked about it quite a bit with venous return. I said, man, if we get more blood in the heart, we have more blood inside the heart. Well, man, more blood's going to be able to get pumped out of that heart too. So at the very end of diastole, purple, 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 boom, there's green. That's the very end of diastole, right? That's where the maximum volume of blood, yeah, that's going to be related to the Frank Starling law, Andy. Good, 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 good. But that's where the maximum volume of blood inside that heart is going to be. Now, atrial plateau, atria contracts. We still got some end diastole that's occurring here, because as the atria contracts, the last of the blood from the atria gets squirted down into the ventricles. So at the very end of this atrial contraction phase, way out here at the end of the green, well, that's when the maximum volume of blood inside that heart's going to be. That's when, oddly enough, ventricular diastole has ended, and you guys are going to see that ventricular systole starts. So diastole is going to occur all the way until ventricular systole starts. Well, when is ventricular contraction going to start? Only once electricity makes it down into the ventricles. True story? So what's happening at the very end of atrial contraction, ventricular filling? What's happening at the very end of that PQ segment is now we got the QRS. And the Q and the R, this is where it's now spreading out through the interventricular septum. And this is what I'm talking about, it's electricity. So that action potential is depolarizing the interventricular septum, and it makes it to the apex of the heart and starts spreading out through ththose Purkinje fibers. It's going to start spreading out through those Purkinje fibers. Now, the ventricles, if you remember, I talked about this when we were talking about the EKG. Yes, they're going to start to contract, but are they fully contracted at this point? No, because it's just starting to depolarize. So maybe some of the ventricular myocardial tissue is depolarized enough for a plateau phase to begin, but not all of the ventricle. Does that make sense? Because that electricity hasn't spread out through all of the Purkinje fibers. Yes, no, maybe so? So what you're going to end up finding is that there's a term called isovolumetric contraction we're going to learn about in just a minute. But eventually, the pressure inside of those ventricles is going to build up, build up, build up. As that heart contracts, as the contraction is just getting more and more forceful around that ventricular chamber, eventually the pressure gets so high that blood is just going to get pushed out into the aorta. This is called ventricular ejection. We're going to learn more about that, but that's all occurring during ventricular systole, the blue in this. What color would you guys say this is? Gold, tan, beige, puke? I love it. Okay, vomit color. Great. My daughter vomited all last night. All right, cool. All right, ventricular repolarization. Well, what's going to finally get to happen after the ventricles start to repolarize? Well, that's where the calcium starts getting pumped out. Now, is it just immediately pumped out, or does it take time to remove all of that calcium? It takes time to remove all that calcium. Takes time to remove all that calcium. So eventually, what you're going to end up seeing is the purple is where all of the calcium's been pumped out, and that ventricular muscle is fully relaxed. That's ventricular diastole. So it's pretty cool the way that they all line up. You can see the blood flow through these chambers with this particular picture. But where it really starts to both click and be a little bit more confusing are with these graphs down here. Now, you will not, let me repeat, you will not have to replicate these graphs. Is that clear? You're not going to have to draw these graphs. I used to make students do that when we only taught anatomy as a separate course from physiology because there was enough time for it. This is a really cool thing to learn to draw, and it's a great thing to study, but you will not be asked to replicate this at all. However, I want you guys to look at this graph. I want you to look at the x-axis. It's time. So this is what's happening in the heart over time. This is one cardiac cycle, a single cardiac cycle, which means one contraction, one relaxation step. Okay, one contraction, one relaxation is one cardiac cycle. A cardiac cycle, one contraction, one relaxation. And the way it all works is, as we've been discussing, electricity, which is the EKG, is going to end up resulting in a mechanical event. So we can look at the EKG to look at what's happening with electricity, but then we can actually look at what's happening physically to that heart. So what's the function of the heart? Cardiac output. It's to pump blood, right? That cardiac output is coming from the ventricles. It's not coming from the atria. Does that make sense? The cardiac output's coming from the ventricles. It's blood that's leaving the heart. And blood leaves the heart from the ventricles. Blood does not leave the heart from the atria. Yes, no, maybe so? Now, when blood gets jacked out to the rest of the body versus the lungs, which one's going to require more pressure? Blood leaving from the right ventricle to the lungs, or blood leaving from the left ventricle to the systemic circuit? So left side of the body requires a lot more force, a lot more pressure. Does that make sense? In addition, when we take somebody's blood pressure, which system are we talking about? Pulmonary circuit or systemic circuit when you're taking somebody's blood pressure? So what side of the heart are we dealing with when we're looking at somebody's systemic blood pressure? We're primarily trying to reference the left side of the heart. Finally, which one do you guys think is more critical medically speaking? Which one do you guys think fails more often than the other? The right side of the heart, which doesn't really do a whole heck of a lot for pressure anyways, or the left side of the heart with massive amounts of muscle. And if something fails, lots of things can go wrong. So this Wiggers diagram, what you'll notice is focusing on the left side of the heart. You guys see that? It's looking at the left atrium here with the green line. The blue line is the left ventricle, and the aorta is the red line. That's all referring to the left side of the heart and the systemic circuit. Does that make sense? And we're looking at the left side of the heart because the left side of the heart tends to be more critical. So for those people going into sonography, this is going to be a big part of your future, is doing echocardiograms, where you're doing these, sonograms on people's heart, and you're literally measuring the volume of blood inside of that heart, and you can start to determine how much pressure is being applied inside of that heart. And I'm not going to go, so you guys can all kind of start to ignore me except for people that are super geeky. These are called PV loops, and PV loops are determined because of our echocardiograms, where we can look at pressure volume relationships inside of the heart, and they're super duper 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 cool. And it's really easy to start to determine different types of heart failure by looking at a PV loop, and that's all determined by echocardiograms. So, and the sonographer is the one that does the measurements, and a little mistake can end up with a big time problem. So sonography's crazy. Okay, so what does this all mean? Let me simplify maybe simplify the heck out of it. I don't know. I think it simplifies the heck out of this thing. Let's look at a door. We've kind of done this already this semester, by the way. We talked about doors that are on hinges. How can we open up a door with a hinge? We're going to need to apply enough pressure on one side of that door to open that door. So as long as the pressure is greater on this side of the door relative to this side of the door only opens in the direction of the arrow. What do we know about this door? If the pressure is greater here relative to here, will that door be open or close? Again, if the pressure is greater on the left than the right, will that door be open or closed? Let's go, peeps. Open or close. It's a simple, 50-50. I'd love more feedback here so we can get moving. So only got 4 people, 5 people, 6 people. Perfect. Okay, whatever. We're there. Let's try to get a little bit more on spot here. I'd love to get you guys through this material. So that would be open, right? Well, let's think about something else we learned earlier this semester that plays right back into heart, which is blood flow. Do you guys remember that big long blood flow chart you guys learned about, where blood's going through inferior, superior vena cava, down into the right atrium, down into the right ventricle? It was on the exam. I had to go through the tricuspid valve first, out through the pulmonary semilunar valve into the pulmonary trunk. Yeah? That's the right side of the heart. So if we wanted to simplify the left side of the heart, let's start with the left atrium. Where's all that blood going to be flowing into? From the left atrium, it's going to be flowing into the left ventricle. Sweet. Easy peasy, lemon squeezy. And from the left ventricle, where's all that blood going to be going to? Perfect. Aorta. Good. Does this flow chart make sense to everybody so far? Simple, 3 chambers that blood can go into. Now, valves. What valve did we have between the left atrium and the left ventricle? We'll be consistent here. It's always try before you buy. This is the left side of the heart. So you guys might have just got a little confused because you're thinking tricuspid comes first, but this is the left side of the heart. So we're over at the bicuspid valve. Does that make sense? Yeah, it's an easy one to mess up at first. It's just one you gotta kind of, as you study it, bicuspid valve. Now, we'll end up just saying this is probably we'll just abbreviate it as BV from here on out because room reasons. Next, over here, left ventricle is pushing blood out through which valve to get to the aorta? Aortic semilunar valve. Good, 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 good. And I don't necessarily always like to do this because it is the aortic semilunar valve, and I actually took points off of some people's lecture exams on this. So I don't refer to it as the AV valve because AV valve is also the abbreviation for the atrioventricular valve. Now, if you're in a medical setting, they often refer to this valve as the aortic valve or the AV valve. Again, I don't like that reference because it takes me back over here to the tricuspid and bicuspid valves. So we'll be abbreviating this as ASV. So what I want you guys to see with the graph here is that there are 3 lines. Got a green line. What are we referring to? The left atrium. I got a blue line, the left ventricle, and I got a red line, which is the aorta. Sure looks a lot like the flow chart we just drew. Left atrium, the left ventricle, and the aorta. Yes, no, maybe so? And we know that each one of these has a valve in between them. And we know that these valves can only move in one direction. So when will the bicuspid valve be open? It's all related to pressure gradients. It's all related to pressure gradients. So let's put a little table over here. Let's start thinking about pressure gradient differences. Okay, so if I'm talking about the atrial pressure, I'm just going to write in atrial pressure. We know at this point we're talking about the left atrium, but this would also work in the right atrium. It doesn't really matter. So atrial pressure versus ventricular pressure. Versus aortic pressure. And let's use some greater than or less than symbols to try to understand what's going on here. So if atrial pressure is greater than ventricular pressure, what do we already know about the bicuspid valve? Will it be open or will it be closed? So we're going to write BV. We're going to have a column over here, BV, and we're going to have a column right next to it, which is ASV. We'll be thinking about what's happening with each one of these valves. We'll just have this kind of separated from everything else. And the whole idea here is whether the valve is open or closed. So as long as atrial pressure is greater than ventricular pressure, that means that the atria is pushing towards the ventricle. And if the pressure is greater on this side of the door relative to this side of the door, will that valve be open or closed? I got a lot of opens already. You don't have to re-answer it if you don't want to. But yeah, in this scenario right here, the bicuspid valve is open. What about the aortic semilunar valve? If the ventricular pressure is less than aortic pressure, will the aortic semilunar valve be open or closed? Go O or C for me, pretty please. Next scenario. stick with the color. So now let's take atrial pressure. And ventricular pressure. You're going to see that this is the same format no matter what we do. And aortic pressure. So you can write this, 5 times if you want. We'll get through each one of these scenarios. But now let's imagine that the heart starts to contract. Okay, at first, atrial pressure is greater than ventricular pressure because the ventricles aren't contracting. Think about it. The ventricles are these big, huge, thick muscles, but if they're super duper relaxed, they have very little pressure in them. But now these ventricles start to contract. Yes, no? Force of contraction going up because calcium is entering these cells. And the pressure inside that ventricle is going to shoot through the roof. The pressure inside that ventricle is going to get super big. So right off the bat, the ventricular pressure is going to get greater than the atrial pressure. As the ventricles contract, the ventricular pressure gets greater than the atrial pressure. Yes, no, maybe so? And what's going to happen to the bicuspid valve when that happens? When ventricular pressure gets greater than the atrial pressure, that bicuspid valve is going to close. Now, it doesn't just close. Here's the deal. It doesn't just close. It actually, bye, Andy, you're welcome. Come back and watch this. It doesn't just close. It slams shut. It's a door. Go to your own door and shut it with a lot of pressure. Are you going to hear a noise if you slam your door shut? Probably. This is the first heart sound. If you're listening to a patient's heart, lub-dub, 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 that first heart sound you hear is the slamming shut of the bicuspid valve right here, because it's the first valve that gets slammed shut. This is called S1, right? This is sound 1. Now, the heart is just starting to contract. The heart is just starting to contract. So the pressure inside the ventricle isn't that great yet. It's just greater than the atrial pressure. So ventricular pressure here is still going to be less than aortic pressure. And I'll come back and I'll give you a reference to why aortic pressure is higher. We'll go back and look at that graph real quick. But let's go ahead and fill this in. If aortic pressure is still greater than ventricular pressure, will that ASV be open or closed? It's still closed. Wait a minute, I got a problem. Look at what's happening to all the valves in the heart. Every valve inside that heart is currently closed. So can blood move around if all the doors are closed? No. The blood is actually going to become stagnant during this time. It cannot move. So let's go back to the graph and let's look at these first 2 points that I just drew in here using this, quick flow chart, table, diagram. I don't know, something I invented. It works though. And let's look at the first 2 steps that's occurring in this heart. So the very first thing is that the heart is relaxed. It's chilling here in purple. This is diastole. And during diastole, what do you notice about the green line and the blue line? Which one is above the other one? Is green greater or is blue greater? Oh my gosh. So in green is atrium, and therefore, if we read this, this is pressure of the atria is greater than pressure of the ventricle. During this period of time, the green line's greater than blue line. Yes, no, maybe so? And that's exactly what we have here. The atrial pressure is greater than ventricular pressure. And what do we know about the valves as long as the green is greater than the blue? What do we know about the valves? Which valve is open? Which valve is closed? Which valve is open? Let's just go there. Yeah, the bicuspid valve is open. So during this period of time right here, As long as the green is greater than the blue, the bicuspid valve is open. And as long as the bicuspid valve is open, can blood move from the atria into the ventricles? Yes or no? The bicuspid valve's open. And check it out. That's when the heart is filling with blood. This is ventricular volume. So as long as the bicuspid valve is open, blood can enter the ventricles, and this value goes up. Does that make sense? Now, what's going to happen? What's going to happen? Well, the heart's going to get current. And the very first part of the heart that contracts is the atria. And so the atrial pressure is still greater than ventricular pressure as the atria are contracting because the ventricles are still totally relaxed. So this little blip right here is when the atria contract, and the last of the blood gets squirted into that ventricle, which causes ventricular pressure to rise ever so slightly because the volume just maxed out. And diastolic volume just occurred. This is the maximum amount of blood that the ventricle can fill with during this cardiac cycle. So now current goes flying down through the interventricular septum and into those Purkinje cells, and those ventricular contractile myocardial tissues start to contract. They start to contract. So what's going to happen to pressure inside of that chamber as the muscles start to contract? What's going to happen to pressure? Increase, decrease, no change. In the ventricle. Yeah, of course. Now it doesn't just shoot up to like 100%, right? It takes time. It's ramping up pressure. Does that make sense? But right here, as that ventricle contracts, right here, right at this point there, I just drew this little circle, all of a sudden ventricular pressure got greater than atrial pressure. True story? The blue just got bigger than the green. So what do we know? As long as the blue becomes greater than the green, blue is ventricular pressure, as long as ventricular pressure gets greater than atrial pressure, what just happened to the bicuspid valve right at this moment? Right at that moment right there. And it doesn't just close. Remember, it slams shut. I mean, you can write C as in close. That's fine. But in your brain, be like, man, this is making a noise because there's some anger management issues going on right now. All right, doors are getting slammed. This is S1. Now, the last part of this has to do with aortic pressure. Don't overthink this. Stop looking at everything. Just follow my voice and look at what I ask you. Aortic pressure. The maximum pressure you see on this graph is what? For the red line. Follow it over and tell me what the maximum pressure for aortic pressure is that you see here. 120 millimeters of mercury. Does that make sense to everybody? If you take this red line, follow it on over, it's about 120, 118, 120-ish. What's the minimum value that you guys see here? The minimum value that you all see here, follow it over, what do we got? 120 max, 80 min. Does that sound like something you guys learned about before? What? What does that sound like to you? Oh, that's your blood pressure. And isn't blood pressure a measurement of pressure in the systemic circuit? Yeah? So those pressures are also the pressure gradients that the heart has to push against. It's a pretty cool idea. Aortic pressure is almost always going to be greater than the ventricular pressure because ventricles are this muscle that's going to relax. And as long as it's relaxed, ventricular pressure is less than systemic pressure by a long shot. I mean, it's nearly zero down here at the bottom, for Pete's sake. Ventricular pressure is often less than aortic pressure. So even as the ventricles start to ramp up, the pressure is ramping up, but it's still not up to 80 millimeters of mercury. It's just not there yet. So ventricular pressure is still less than aortic pressure. Ventricular pressure, the blue line, ramping up in pressure, but it's still less than the red line. Everybody see that? So what do we know about the bicuspid valve? It's slammed shut down here. What about the aortic semilunar valve? Is it open or closed right now? As long as ventricular pressure is less than aortic pressure. Is it open or closed? Yeah, it's closed because we know ventricular pressure is still less than aortic pressure. Make sense? And one last little bit here that references back to something we just learned about. What do we know about volume during this time? If all the doors are closed, can any blood enter? Can any blood leave? This is called ISO. ISO in Latin means same. ISO means same, just like isotonic, isotopes, all the ISOs out there in the world means same. Isovolumetric means the volume remains the same during this time. Does that make sense? So write down that word. It's called isovolumetric. Isovolumetric. And are we in the middle of contraction or are we in the middle of relaxation right now? Do we have ventricular systole or are we starting ventricular diastole? What's going on? So that's why this is called isovolumetric contraction. It is currently contracting, Heather. It's not about to contract, it is contracting. It's just slowly contracting, it's ramping up. Not all the muscles are in the process of contracting. Some still need to get electricity. Does that make sense? It's not about to contract, it is contracting. Otherwise, muscle couldn't be building up pressure. Okay, cool. Now, what's going to end up happening is that heart is going to contract slowly, but eventually the heart is fully contracted, right? During this time, these muscles are just squeezing down on the chambers on the inside. So let's draw something here. We know atrial pressure is still stupidly low because we're still contracting. So those atrial pressures are still much less than the ventricular pressures because those ventricles are just contracting like crazy. But eventually, what's going to happen to the ventricular pressure is it's going to, due to these massive muscles of the heart, it's going to cause the pressure inside of that left ventricle to suddenly become greater than the aortic pressure. That ventricular pressure is going to become greater than 80 millimeters of mercury. At which point, what's going to happen to the aortic semilunar valve? The second ventricular pressure gets greater than aortic pressure. Now that guy is going to open, right? The aortic semilunar valve opens up. Can blood leave the heart now? I'll get back to that, Heather. Blood can now leave the heart. Now think of this like a water balloon. If you squeeze a water balloon and squeeze it and squeeze it and squeeze it until the pressure inside that water balloon becomes so great, what's going to happen to that water balloon? And all of that water is going to go bursting out of that water balloon very fast, right? Because of all the pressure that was building up. Well, thank goodness your heart doesn't burst, it doesn't pop. But when that door opens, that's going to cause a veritable flood of blood to leave that ventricle in a rush. That's why it's called ejection. This is an ejection of blood. It's a get the GTFO, right? So this area right here under the curve is when blood is physically getting moved out of the heart due to the pressures being so high. So we call it ventricular ejection. Is that clear? And again, what do we know about the pressure gradients? As long as the ventricular pressure is greater than the aortic pressure. As long as the blue line is greater than the red line, then the aortic semilunar valve is open and blood can be leaving the heart. And look down here on the ventricular volume curve. Do you see how ventricular volume is decreasing? Because blood is leaving the heart, so there's less blood in the ventricle. Yes, no, maybe so? But what's going to happen eventually is that ventricle is going to start to relax. It loses its current. The L-type calcium channels start to close. The ryanodine receptors start to close. The calcium pump is moving calcium out of the ICF. The NCX is doing its thing, right? Exchanging sodium for calcium, and calcium levels in that ICF start to drop. So what's going to start happening to the force of contraction as calcium is removed? It's going to drop. Yes, no, maybe so? So now we got to go back here again, and we got to write in atrial pressure. We get to write in ventricular pressure. Trying to go fast for y'all here. And we're going to go aortic pressure, of course. Same pressures every single time, and all we're doing is we're changing the pressure gradient. So at this point, ventricles are relaxing, but their pressure is still greater than atrial pressure. These guys over here, these are the wimpiest of the wimp. Ventricular pressure, though, as the ventricles relax, well, they're going to drop below aortic pressure. And again, when you shut a door, you're shutting it with a lot of force. Bicuspid valve is still closed, but the aortic semilunar valve is going to slam shut. And this is where that second heart sound comes into play. This is S2. Lub-dub, 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 lub-dub. Those are the slamming shut of the valves. There are actually other valve sounds that you can hear, but these are the two major ones. You have to have a really good stethoscope and be hella good at hearing sounds to be able to find some other heart sounds in there. But don't want to hear lub-dub whoosh, by the way. That's bad. That means blood's flowing in the wrong direction. Did that make sense? And since all of the valves are closed, can blood leave or enter? We'll get there, Melissa. Can blood leave or enter the heart while all those valves are closed? No. So we again call this isovolumetric. Iso meaning same, volumetric meaning that the volume inside of the heart is remaining the same. So where on the curve is this? This is right when ventricular pressure gets less than aortic pressure. Literally right at that point. Right there. When ventricular pressure gets less than aortic pressure, that's when that aortic semilunar valve is going to slam shut. And that ventricle is relaxing. It's chilling out. But that ventricular pressure is still greater than atrial pressure, even though it's less than aortic pressure. So all the valves are closed right here. Isovolumetric. Did that help answer your question from before, Heather, with the repeat of what is isovolumetric? Perfect. That's why I held off until now. But is the heart contracting or is the heart relaxing right now? It's relaxing. So we call this isovolumetric relaxation. If you look down here at ventricular volume, there's something interesting. At the very start of, I just glitched. You guys hear me okay? I know I glitched on my side because I get feedback. Cool. Can you guys see my screen okay? Awesome. Okay, so at the very end of diastole, or at the very beginning of systole, that's where we have this maximum volume of blood in the heart. We called it EDV. But check it out. as the heart contracts, right, and it's only going to be contracting here and then relaxing here, there is a time when ventricular pressure gets greater than aortic pressure that blood is rushing out of the heart. So through this entire time of ejection, blood is leaving the heart. But can any more blood leave the heart once ventricular pressure gets less than aortic pressure? Can blood leave the heart anymore? Yes or no? The answer is no. All the valves are closed at this point, right? Most importantly, the aortic semilunar valve is closed. And as long as the aortic semilunar valve is closed, nothing can leave. And therefore, at that point, we are at what's called end systolic volume. Okay, this is the minimum volume of blood left inside of the heart. We're going to come back and write those two things down, end diastolic versus end systolic. But something I want you guys to note right now, you can circle this on your guys's, I don't know, printouts, diagrams, however you want to do this, is end systolic volume is not 0. Do you guys notice that this weird y-axis over here doesn't go to 0, 0? It actually goes down to 70. So maximum in a normal person is about 130 mils, minimum is about 70 mils. So does the volume of blood in the heart ever reach 0? Hell no. Okay, there's always about 50% blood left over. We do not empty the chambers of the heart when we contract. We want about 50% of that blood left over. 50 to 40% of that blood should be left over. We never want to empty that blood all the way out. We always want to reserve. So now if we need more blood and I contract a little bit harder, what's going to happen to the end systolic volume? If I just contracted the heart just a little bit stronger, pressures go up. What's going to happen to end systolic volume? Increase, decrease, no change. As more blood gets ejected. It's a tricky one because end systolic volume is not the amount of blood that's ejected. That's stroke volume. The end systolic volume is the volume of blood left over at the end of contraction. So if I just contracted harder, do you guys see how there would be less blood left over? So it would be a decrease in ESV. Yes, no, maybe so? It's a little tricky, but definitely doable. The heart contracted stronger, more blood gets ejected, so there's less blood at the end. So the end systolic volume would be lower. If you didn't catch that, think back through it, watch that part of the video again, see if you can slow yourself down and think about how that works. Well, finally, I mean, the ventricles are they're just relaxing like crazy. Just relaxing, 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 and then look what's going to end up happening. Ventricular pressure, blue line, is going to drop below atrial pressure, green line. Ventricular pressure is still a lot less than aortic pressure because the ventricles are relaxing. Aortic pressure is very big. The big difference here is now ventricular pressure just dropped below atrial pressure. In other words, atrial pressure just got greater than ventricular pressure again. So the aortic semilunar valve still closed, but what's going to happen to the bicuspid valve? The second that atrial pressure gets greater than ventricular pressure, what's going to happen to that bicuspid valve? It opens back up. Now, can blood start to enter the left ventricle again? Yes, no, maybe so? If that bicuspid valve is open, can blood enter the left ventricle? Lovely, perfect. So let's go ahead and label each one of these points because we need to. Over here, atrial pressure is greater than ventricular pressure, is less than aortic pressure. At this point, the heart is kind of relaxed, right? This could be a aortic systole, as long as the aortic, I said aortic systole, sorry. This could be atrial systole, or this could be ventricular diastole. It can be any part of this curve where the green line is greater than the blue line. So that green line is greater than the blue line all through here. The green line is greater than the blue line all through here as well. So as long as the green line is greater than the blue line, then the heart is refilling with blood. Does that make sense? Because that bicuspid valve is open. So during this period of time, refill. Refill, refill, refill. Now, again, this could, you might want to write in, this could be ventricular diastole, or this could be atrial systole. It doesn't matter. Now, what does matter are the next few. Atrial pressure is less than ventricular pressure is less than aortic pressure. So what's happened here is that ventricular systole has started. The ventricles are starting to contract. But ventricular pressure is still less than aortic pressure, so all the valves are closed. We call this isovolumetric, ran out of room, contraction, because this is while that heart is contracting. So it's IVC, that's the abbreviation, IVC, isovolumetric contraction. Eventually, ventricular pressure is going to become greater than aortic pressure, so that aortic semilunar valve is going to open, at which point blood can finally leave the ventricles, and we call this ventricular ejection. But hearts can only stay contracted for so long. Eventually, they're going to start to relax, at which point the ventricular pressure is becoming less than aortic pressure again, and then aortic semilunar valve is going to slam shut. All of the valves in the heart are closed, so we have another isovolumetric. But now this isovolumetric is occurring during relaxation. So now we have IVR. Make sense? And right after IVR, we're going to get back to a refill stage. As long as that bicuspid valve is open, the ventricles can refill with blood. So we're going to go ahead and write refill. This is, you know, if we look at this as chronological order, this right here is going to be ventricular diastole. Because what occurs right after isovolumetric relaxation is the ventricles finally are fully relaxed, and this is going to be ventricular diastole. This is when that heart's refilling with blood. Ventricular diastole, we cycle all the way back because this is one cardiac cycle, and technically this would be during atrial systole. But it don't really matter, because no matter where we're at in ventricular diastole or atrial systole, atrial pressure is greater than ventricular pressure is less than aortic pressure. Atrial pressure is greater than ventricular pressure is less than aortic pressure. They start the same and they end the same. Make sense? Awesome. How do you guys feel about this? Is what you need to know for the exam right here. You don't need to know the graph or anything, but the graph helps you understand what's going on here, and this helps you understand what's going on with the graph. So they're very helpful hand-in-hand things, but I won't make you replicate the graph, but like in your lab report, you definitely have to replicate this, and then for your lecture exam, you're going to need to understand what direction blood is moving due to pressure gradient changes. So you need to know exactly what valves are open, exactly what valves are closed, and what direction blood is flowing based on pressure gradients. Okie dokies? It's exactly what we just did. Exactly what we just did. Exactly what we just did. Awesome. Well, we are so close to being done. You guys go ahead and listen to this on your own time because I won't come through my speakers, but I got the first sound, the second sound, lub dub, lub dub, lub dub, lub dub. It's these slamming doors in the heart. So pretty darn cool to see this, right? Look, atrial contraction, then ventricular, atrial, ventricular, atrial, ventricular. And what's happening is contraction or relaxation longer. Look at contraction is done. Or fill, contraction, fill, right? You can see that relaxation, it's refilling with blood. I love this little video. It's cool, super cool. I didn't have anything like this when I was in school. These animations didn't exist. Actually, let's go back to this real quick. What's going to happen between this step and this step is that this heart has refilled with blood, and in the isovolumetric contraction, no more blood can enter that heart. True story? Because all the doors are closed. Nor is any blood leaving the heart because all the doors are closed. So it's right here between these 2 points that we get a maximum volume of blood known as EDV. Is anybody confused by that? Let me know now. I don't mind. And if you're confused, somebody else is probably confused. But this is when the end diastolic volume occurs. This is when the blood in the ventricles is at a maximum volume. No more blood can enter, no blood can leave yet, so it's at max. Well, finally down here during ventricular ejection, blood can leave. So the volume inside that heart is dropping as blood leaves to the aorta. And that's going to be occurring through the entire ventricular ejection phase. The stronger the ventricular ejection, more blood gets ejected. But at the end of ventricular ejection, when the aortic pressure becomes greater than ventricular pressure again, all those valves close and we go back into an isovolumetric stage. So again, all the doors are closed, no blood in, no blood out. And so this, between the ventricular ejection and the IVR, that's where we're going to have the minimum volume of blood inside that heart, known as ESV. And then through the rest of this time, blood is refilling, blood is refilling, blood is refilling. And in the end, we're going to get a maximum volume. Then it contracts. We're going to get a minimum volume. Blood refills, max, min. Does that, you guys with me on a cardiac cycle? You guys see how that works? Love it. Now, if we contract the heart, we have a maximum volume to begin with, we contract and we eject the volume of blood and there's a minimum volume left over. Well, what if we can measure that maximum and we can measure that minimum? We can. This is again with sonography. This is a very possible thing for us to do. We can measure EDV, end diastolic volume, which is the max value. And we can measure ESV, which is the min value of blood, right? This is a blood volume. Ah, that's not blood volume. There we go. Now, what's the difference between these two things going to be? If we have an EDV, a maximum volume, and we get rid of a certain amount of blood and we left with an ESV, if we have a max minus a min, what's that going to give us? That's going to give us the volume of blood that was ejected, won't it? If we start with a maximum volume, this is just a column, and we look at that column, the exact same height of a column. Okay, this would be the total volume that can enter the blood, or sorry, enter the heart. But it's completely filled at EDV, but after the heart contracts, there's still some blood left over, but not a whole heck of a lot. So there's a minimum value that's here right now. True story? And then you can see this is empty volume. So there's no blood there. Yeah. You guys with me? Just a little column, pretty easy, hopefully. If not, I can explain it to you guys during office hours or whatever. And now we take the difference. If we look at what was ejected, well, that difference there, EDV minus ESV, that's going to be how much blood was ejected during a single cardiac cycle. Didn't we define something as the volume of blood ejected during a single cardiac cycle? Haven't we done this like since the beginning of the cardio unit? It's all right. You guys are trapped on this somehow just because you kind of haven't been. There we go. Yeah, exactly. This is SV. This is stroke volume. That's exactly what the definition of stroke volume is. The definition of stroke volume is the volume of blood ejected during a single cardiac cycle. So stroke volume is equal to EDV minus ESV. So we can actually measure a patient's stroke volume using sonography, an echocardiogram. We can get a direct measurement of their SV. Can you measure your patient's heart rate? Hell yeah, you can. So can you actually get a direct and accurate measure of a patient's cardiac output? Yes. Does that make sense? We can measure the volume of blood before contraction. We can measure the volume of blood after contraction. So we can calculate stroke volume, and we can measure a patient's heart rate pretty easily, and cardiac output's just equal to heart rate times stroke volume. And we can get a measurement of a patient's cardiac output. It's pretty cool, huh? I think it's super cool. So again, I'm not going to make you guys do tons of math, although, I mean, there are some normal values. So normal EDV is about 130 mils. Normal ESV is about 70 mils. This is just your average. You know, the range, of course, is bigger than this, but this would be the normal person. So in a normal person, what would stroke volume normally be approximately? Just some quick math in your head there. 60 mils. Again, don't forget the units. Don't forget the units. So the normal person, you start with 130 and you eject about 60. Do you guys see how that's not even 50% of the total volume? Kind of crazy. So there's always a lot of blood left over, which is good because then we could take and manipulate that amount of blood left over. But that would be mathematical. I won't make you guys do this. Instead, I'm all about physiology. How can we change stroke volume? We've already done this, by the way. We did this last week. But what would happen to stroke volume if more blood entered the heart before it contracted? Increase, decrease, no change. Yeah, more blood in, more blood out. That's the Frank-Starling law of the heart. It has to do with actin and myosin and how actin and myosin overlap. More blood in, the actin and myosin. Do you guys remember actin, myosin? You know, you got your actin, basically like your fingertips here, right? And then you got your myosin, and they overlap. And the myosin heads interact with the actin. So I want you guys to look at this. If I'm like this, and the myosin heads can't interact with the actin, how much force am I going to be able to create? None. And what if I take and I over-contract my muscles and I'm hitting the M line? The M line is a solid block of proteins. Can I contract this muscle anymore? So how much additional force can I produce? 0. So the way that actin and myosin works is it's got an optimal overlap. And as actin and myosin overlap each other just right, Goldilocks the shit out of this, then we can get maximum contraction from those muscle tissues. And the only way that happens in the heart is if blood fills that heart. And as blood fills, it's going to put those actin and myosin in this perfect overlap to get the maximum contraction from their next contraction. Crazy. Frank Starling law of the heart. But again, more blood in, more blood out due to this overlap of actin and myosin. Okay? And this is one of the main things that gets impacted in heart failure patients is if their actin and myosin don't overlap properly anymore, then they're not going to refill with blood properly anymore, and they're not going to be able to contract quite as well anymore. So lots of craziness going on there with heart failure. But this isn't a patho class, so I'm not going to go through all the different types of heart failure. Let's keep looking at here. So less blood enters the heart, that's going to drop stroke volume as well. Now, mathematically, that minus sign is a little tricky for students. ESV is end systolic volume. So what if there was more blood left in the heart after contraction? What happens if there's more blood left in the heart? What if this value here was greater? What happened to stroke volume here? If ESV increased, because there's a minus sign, that's going to have the opposite impact on stroke volume. Does that make sense? If EDV goes up, stroke volume goes up, but if ESV goes up, stroke volume goes down. So this would be a scenario where that heart refilled with blood, but it had a weaker contraction. And if it has a weaker contraction, then there's more blood left over at the end of that contraction, which indicates that there's less stroke volume. Does that make sense? You guys rock. We can calculate mathematically a fraction of the amount of blood that's been ejected. A fraction's a percentage, if you think about it. A fraction's just a decimal place, but you multiply a fraction by 100 and you end up with the percent. Maybe makes sense to y'all. I don't never assume anything with math anymore. We call this an ejection fraction. Okay, ejection fraction is the fraction of blood that was ejected relative to max. Whatever that patient's maximum blood is, how much blood got ejected? 50%, 40%, 60%? How much is left over? How much was ejected? Does that make sense? Cool. Now, what do you guys start thinking about ejection fraction? What if a patient had 50% ejection fraction? That means 50% of the blood was ejected, and that means 50% is left over. Not too bad, right? Based on everything we've been learning, that sounds goodish. What if a patient has 35% ejection fraction? Did the heart just get better or did the heart just get worse? Yeah, it got worse, right? Less blood got ejected. %60 ejection fraction, more blood gets ejected. We cool on that idea? So how can we go about calculating ejection fraction? Well, ejection fraction is a cool little thing here, and I got a it's on the Where did I move it to? I think I moved it actually to this particular lecture. I did at the end here. So ejection fraction is a pretty interesting one because what we're doing is we're taking EDV and we're saying, what is the maximum volume of blood that was there? And of that maximum volume of blood, how much was ejected? Okay, so when we go to write down the formula for ejection fraction, we just abbreviate it EF. And EF is going to be something divided over the maximum volume. We always want to say how much is being ejected relative to the maximum that was there. And what value do we know is the value for the volume of blood ejected in a single cardiac cycle? Exactly. So we want to say how much blood was ejected relative to how much blood we started with. Do you guys see how this formula can be defined? It's the volume of blood that was ejected relative to how much was their maximum. And so if the heart beats weaker, we might have plenty of blood in it to begin with, but if it beats weaker, stroke volume starts to drop. Does that make sense? And if stroke volume starts to drop, well, what's going to happen to that patient's ejection fraction as it pumps out less and less blood? That ejection fraction, increase, decrease, no change. Yeah. So really when it comes down to it, the national, I looked all this up, I don't know, 2016, I think. So this value could have changed a little bit in the last 5 years, but national average is somewhere around 52% ejection fraction. But I want you guys to look at this. This is also from the, the National Cardiac Site. There is a range that you can have. Normal function is 55 to 70%. What's the national average? Yeah, Heather, we'll talk about that. So look at the national average. It's 52%. So it's considered high-low function. So the national average, our hearts are, we need some love. Okay, we're healthy. We're not at 40, but our population could do a better job taking care of themselves. That's for sure. Normal functions 55 to 70%. Now, I want you guys to start thinking about what Heather asked about athletes. What's going to start happening to an athlete that's training their body, and at the same time that they're training their body, they're training their hearts? A heart is a muscle. So just like if you did tons of bicep curls, what's going to happen to your biceps brachii if you just work it every single day? That muscle gets bigger. The heart's the same way. If you overwork a heart muscle, it will get bigger. It's called hypertrophy. Hyper, up, above, right? Hypertrophy. It's exercise-induced cardio hypertrophy. And that muscle gets stronger. I love if there's two hearts. That'd be cool. And so each contraction of that heart, what's going to happen to the stroke volume if that muscle is stronger? Yeah, their EDV might not change. I mean, a heart is a heart is a heart. The volume entering that heart, not always greater or less than. You can start getting such massive hypertrophy that it can actually decrease the ventricular volume space, but that only occurs in a disease state. Good, though. So the muscle just got bigger, exercise-induced cardio hypertrophy. And now it beats stronger. So more blood leaves. And what's going to happen to that patient's ejection fraction? Increase, decrease, no change. Good. So as somebody is a extreme athlete like Lance Armstrong, each time their heart beats, Michael Phelps, each time their heart beats, more blood is ejected out. They're an elite athlete. They've trained themselves to a super high function. Yeah, Bolt. Bolt's a rock star. Does this make sense? What's going to start? Do I really want to go here? I do. What's going to start happening to that patient's heart rate, though? If each heartbeat sends out more blood, what do we know the function of the heart is? It's cardiac output, right? So if we have cardiac output equals heart rate times stroke volume, and we have an elite patient, an elite athlete, not an elite patient, all patients are elite, an elite athlete patient, their stroke volume is going to be high. Cardiac output starts to go up. What do we know about homeostasis? Does your body want a super high cardiac output? Yes, no. No, hell no. That could be bad. It can overperfuse tissues, cause edema, kidney failure, all sorts of bad stuff can happen if cardiac output's too high for too long. So what's the body going to try to do to compensate? Going to drop that heart rate way down. So somebody like Lance Armstrong, let me go look this up again, but I believe Lance Armstrong's resting heart rate was 36 beats per minute. He is one of the most powerful hearts in the history of the world, I swear. Can you guys imagine 32? I wasn't even accurate. It's not 36, it's 32. Most normal people like me, 70 beats per minute meets my cardiac output demands. For him, his heart beat so strong. Every single beat of his heart pumped out so much blood that he just didn't need a lot of heart rates. Let's go one more thing and then we'll take a break, because I do think this is amazing, and it could possibly be questions in your lab, practical. I do make you guys calculate beats per minute. So make sure you guys, I'll go through one problem with you guys on that too. But before we do that, remember, cardiac output in humans, we can learn a lot by looking at the animals around us. I'm not going to do this with everything that we do, but I sure do love wildlife. So yeah, you're going to hear a little bit of it. Anybody want to guess what the resting heart rate of a hummingbird is? Just guess. Give me a number. Humans are about 60 to 70 beats per minute. Hummingbird. 120. Love it. More. 200. Love it. More. 150. You must have written that after 300. Keep going up, y'all. Right now you're at about a mouse. Mouse is about 300. $9.99. How many jelly beans are in the jar? So far, Tariq is closest. Still not there yet. Now we're starting to get there. It's about 1,200. A hummingbird's heartbeat's about 1,200 beats per minute. So start thinking about the metabolic demands of a hummingbird whose wings are fluttering so fast. How is that possible? Physiology is how it's possible. Physiology, they have different protein pumps that are moving faster, slower, wherever they need to be. They have a smaller heart. It's all about the physiology, right? The physiology meets the demands of that creature. Since a hummingbird has such high metabolic demands, right? All it does is eat nectar all damn day long, right? It's glucose, more glucose, and fructose. The energy demands of the heart are also extremely high. Does that make sense? So what's the biggest animal on the face of the planet? Yeah, not an elephant. Not an elephant. And what kind of whale? Man, I'm just doing this for fun at this point. Some of you are like, I don't care, Dr. H. Well, I do. Deal with it. Yeah, Parker got it. It's the blue whale. Blue whale's like twice the size of a humpback, crazy enough. Blue whales are giant, largest animal in the history of the world, larger than any dinosaur that we know of. Blue whale is the largest animal ever known to man, as far as we know. I'm sure someday we'll actually find Godzilla, and it'll be bigger than blue whale, but whatever. Now, anybody want to guess? What is a blue whale's heart rate? Just guess. Again, just for fun. How many jelly beans in the jelly bean jar? 30. All right, so basically Lance Armstrong. Keep going down, y'all. Keep going down. Keep going down. So they beat about 2 to 4 times per minute. Every single time that heart beats, it's ginormous. A blue whale, let me show you. I mean, it's kind of gross. Do you guys want to see what a blue whale heart looks like? It's a little disturbing because a lot of these are with whalers, you know. But they're so big. The aorta is so big. Good. This one's good because it's actually just a depiction of one. But a large blue whale, and there are large blue whales, you can actually, and these things are big and elastic, you can actually fit a small, like one of those little smart cars into the aorta of a blue whale heart. That's how big they are. And so each time, yeah, it's about 440 pounds just for the heart. It's crazy. It's absolutely crazy. And so each time that heart beats, boom, it's pumping out enough blood to this blue whale to be able to support its cardiac output. It's all about cardiac output. Whatever the energy demands of that animal are, if they're being met, then the heart is going to beat just the speed it needs to beat. It's pretty amazing. It's pretty amazing. Does that make sense to everybody? Perfect. All right, so let's just look at this schedule real quick. We got Tuesday, Wednesday, and Thursday. Yeah, the EKG would look very funny. You'd be like, no pulse. We got Tuesday, Wednesday, Thursday. Wednesday is all about blood vessel anatomy. Okay, blood vessel anatomy is going to be blood vessels 1 PowerPoint. Wednesday's lab, you're going to be learning all of these blood vessels, the names of arteries and the names of veins. I know you guys already have so much to do. I get that. If you get a chance, find some time to look at these lab things before coming to class, before coming to lab on Wednesday. If you get a time, I know you're like, where the hell am I supposed to find this time? The reason why I say that is because don't forget, your homework is already due on Saturday, and your lecture exam and your lab practicals already due Sunday. And I want you guys to look at this lab that we're going to do on Wednesday. It's the longest one that you've ever done in any of your lab classes for A&P. Okay, it's 3 full pages long, all sorts of things from coronary circulation, hepatic portal circulation, some lymphatic system stuff, lots of arteries, lots of veins, and the microanatomy of a blood vessel. So if you get the chance, look at this before coming to lab on Wednesday. And I have other things for you, right? We got just vasculature PowerPoints, lymph node PowerPoints, video of the lymphatic system models, videos of the blood vessel models. So please, I have stuff for you for Wednesday's lab. It's going to be a little overwhelming if you come cold turkey. I understand if you can't. Is that clear? Does that sound fair? Fair enough? I'm just trying to help. Yep, we're in week 4. End of this week, you'll be halfway through the semester already. It all goes so fast. So what we're still going to use a little bit of our time today because of this. I'm so sorry. It's kind of like that, what is Demi Lovato song, Sorry Not Sorry, but like this is what you signed up for. I will give you guys a break. And then we're going to come back to do, and we're going to introduce ourselves to blood vessels, to the physiology of blood vessels. So we're going to come back and be doing this. So please be back at 12:35, 40 minutes. That should be enough time. That will be enough time. Go ahead and take a 20-minute break. Get some food. Go and cuss out Dr. H to your significant others or kids or whatever it takes. Get it off your mind. I've already, a bunch of people are bailing, so I hope not everybody bails. We'll end around 115, 120-ish. Technically, I know the time says online 1, and I don't know why it does that. This class goes to 120 in a regular semester. So, but we'll end somewhere around there. I just need to get blood flow introduced to you guys, and it's not that complicated of an idea, but I also want to give you guys food. So please be back at 40 after. All right. Welcome back to A&P Forever. So just a quick reminder, got YouTube videos for all of this that we've been covering. Everything from EKGs to events of the cardiac cycle Wiggers diagram. All, very similar to what we did in class, but slightly different. It's all here. Everything that we're going to start to summarize over the next few days is also here. From general characteristics of the blood vessels, blood flow, blood pressure, resistance. This is what we're going to introduce today. Baroreceptor reflexes, which you've kind of already looked through. You'll notice that there's a lot of relationship with blood pressure and what's going on in the heart. And then intrinsic and extrinsic controls of blood pressure, which is pretty darn important. And then one of the major extrinsic controls of blood pressure is renin. So all of this is tied in. You have these videos available for you now. So hopefully you guys have started to look through those when you when you find the time. I do feel bad for you. I hope you guys know that. Like, I commiserate with how fast the pace of a summer class is. But again, sorry, not sorry. But I am sorry. But I'm also here to help. I hope you guys can see that. You guys can hear me, right? I hope you guys are noticing I'm here to help. I'm trying to get you guys through this material. I'm actually going slower than a lot of other professors would. Whether you see that or not, I don't know, because actually all of you guys had a different A&P1 instructor than me. None of you guys had me for A&P1. So I hope you guys are seeing that I'm a little bit different. Like, I really want to make sure you guys understand particular ideas that will be on the exam. I test on what I teach. I don't know whether you guys see it different or not. I don't know. All right, moving on. So what we are going to do is introduce a little bit of blood vessel stuff. So I'm going to go into blood vessels 2. Blood vessels 1 is anatomy of blood vessels. Blood vessels 2, 3, and 4 is all physiology. And you guys already have the background to understand a lot of what's going on here. So what's the function of the heart? Go for it. What's the function of the heart? Cardiac output. Easy peasy lemon squeezy. We took a week of learning that, emphasized it extremely strongly. What about vascular, cardiovascular? What's the function of the vascular system? Good, transport blood. You guys got it. That's exactly what it is. It's all about transportation. It's a highway system for blood. And we learned, in Unit 1, what is in blood. So what's being transported? Oh gosh, nutrients and gases and plasma, which is filled with water and proteins, and red blood cells doing their thing, and white blood cells doing their thing, thrombocytes, so forth, so on. So we know blood is pretty darn important for the human body. And these blood vessels are bringing everything where they need to go, whether it's good things in or potentially metabolic waste out. It's definitely part of the whole spiel, shtick. I guess shtick would be a better term for a blood vessel function. Transporting blood. Well, in physiology and physics, when we are moving a liquid, we call it flow. Okay, as any liquid moves, it's called flow. And that's what we're going to be dealing with here at the beginning of the cardiovascular system in terms of blood vessel function. Is what we really want to start to hone in on is, sure, the function of blood vessels. They're all about transportation. You're not wrong even in the slightest. But we want to start to think about this in a physiological context. And as a physiological context goes, if we're moving things, that means that there is flow. Flow of what? Flow of blood. Okay? We need blood flow. We got to have blood flow. Gots to have blood flow. And if we're moving blood from point A to point B, let's take a tube. Let's take a tube, and we're going to move blood from point A, and we're going to move it over here to point B. Everything in the universe around us is trying to move from an area of high to low. What a great place to start with this nice foundational knowledge that you guys hopefully have ingrained in your brain. If I'm going to move something from A to B, what do we know about A? First off, if I'm transporting a fluid, I need pressures. So what do I know about the pressure of A relative to the pressure of B if I want to move it from A to B? What's going to have to happen? Pressure in A bigger or the pressure in A smaller? Increase works for me. I understand exactly what that means. So is A higher or lower? Bigger, smaller, greater, whatever it is. Yeah, I mean, A's got to be bigger. True story? Does this make sense? So let's say, for instance, the pressure over here at A is 120 millimeters of mercury. So work with me. This is not how it is in the human body. Not yet. What if B was 120 millimeters of mercury? Would there be any flow whatsoever in this scenario? No, there couldn't be, right? Because the pressures are equal on either side, so nothing can move from high to low. Does that make sense? So in other words, blood flow is proportional to the gradient for pressure. So if you guys didn't know this, which you probably, I don't know, some of you may have, some of you may not have, a delta sign, this little triangle means gradient. So I'm going to go ahead and give you guys a little key up here. This means gradient, and gradient just means the difference between two sides. We've already defined that earlier this semester. So if I said delta P, what delta P is a pressure gradient. So here an example, whatever, the first example that I did, 120, 120, is there a pressure gradient in this example? Yes or no? No. What is the gradient here? 120 minus 120, it's the difference between two sides. It's 0. And 0, if the pressure gradient's 0, blood can't flow. Does that make sense? So let's start creating a pressure gradient. Now, the pressures out in your tissues are not going to be 120 millimeters of mercury, but what is 120 millimeters of mercury? The pressure in the left ventricle and the aorta, right? So if I had the heart over here, God, that is a beautiful heart. If I have a heart over here, it's creating about 120 millimeters of mercury of pressure during systole. Does that make sense? And so what do you know about the value out here in B? If I'm out in the tissues, is it going to be higher than 120 or lower than 120? Pretty easy idea. Lagging a little bit, I'm sorry. Yeah, it's going to be lower. And the greater that difference, the greater blood flow speed will be. So say for instance, out here in the tissues, I don't know, blood pressure is 40 millimeters of mercury, then the difference is 80 millimeters of mercury. But if, say for instance, in scenario, I don't know, another scenario here, it's 20 millimeters of mercury, well, now the difference is 100 millimeters of mercury. So which one of those is blood going to flow faster? 1 or 2? Which one's going to flow faster? Yeah, you got it. 2, where the gradient, the difference between the two is bigger, blood flows faster. Does that make sense? Now, that's not the only variable that affects blood flow. What is the first variable that affects blood flow? And I want you to think about what is the primary driver of this pressure gradient. The primary driver of this pressure gradient, not really what's happening out at the tissues, because the reality is out here at the tissues, we're going to be looking at minimal changes. Like it's going to change from, I don't know, 20 millimeters of mercury to 25 millimeters of mercury. Oh, we'll come back to hydration in a bit, Heather. You're overthinking my question. I apologize because I haven't fully been able to answer it yet, or ask my question, sorry. Is that if I'm trying to think about what is creating the pressure that is going to drive blood from high to low, where I want to actually look at is at the beginning of the story, because this is where we're going to get our largest pressures that are pushing blood. So what organ of the body is actually creating this pressure gradient? Yeah, it's that heart. The heart creates that pressure gradient. And what is the function of the heart? So in other words, this pressure gradient here that we're learning about is determined by the cardiac output. So if cardiac output were to increase, what's going to happen to the pressure in the aorta right outside of that heart? If cardiac output were to increase, what would happen to the pressure in the aorta right outside of that heart? Increase, decrease, no change. Sweet. We just now have a greater blood flow. Does that make sense? And then, of course, if cardiac output drops, then this blood pressure starts to drop here next to the heart, and the gradient just got smaller, so blood flows a little bit slower. Now, in physics, there's something else at play here. As long as we're inside of a tube, which we are, a blood vessel is just a tube. Tubes across the universe all act the same on a fluid that's flowing through that tube, whether or not that is a pipe that's in your wall feeding your bathtub some water, whether it's a straw, which is the analogy that I end up using the most, or whether it's your blood vessels. Doesn't matter. All tubes act the same. And if I have a tube, which I have drawn right here, and if I have blood, liquid, moving through this tube, the reality is that this tube right here has walls that's exerting forces against the flow of blood through that tube. All tubes in the universe around us create what's called resistance. Okay? Resistance, is basically due to friction. Whereas fluid is flowing by the walls, there's those water properties, water tension, surface tension properties, where the water tries to cling on to the walls of those tubes and it slows it down. So resistance. If something has resistance, is it going to make blood flow faster, or is it going to make blood flow slower? If something has resistance, yeah, it's going to be slower. So is that going to be directly proportional or inversely proportional? Is that going to be a D or an I? Directly proportional or inversely proportional? Not directly. Do you guys remember those terms, right? A equals B over C. B is directly proportional to A, and C is inversely proportional to A. So if B were to increase, A would increase. But if C increases, what happens to A? It does the opposite. True story? You guys remember going through this? So if it does the opposite, what we do in a formula is we put it on the bottom. We put it on as a denominator. So resistance is always opposing blood flow. It's always trying to do the opposite of blood flow. Yes, no, maybe so? This is R, which means resistance. Man, I did not even come close. Resistance. Anyways, you guys get the point. Now, resistance has some variables that impact it. And in tubes across the world around you, there are some factors that we can think about that create resistance. So the one I like to use the most in my class is trying to drink through a straw. And, you know, not that too many people drink margaritas through a straw, but it can be pretty fun depending on the type of margarita that you got. So my margarita analogy comes into play here. Now, if you've never had a margarita, well, I don't know what's wrong with you. I'm just joking. It's okay to each their own, but almost everybody's had a shake, right? Like a chocolate shake. So the analogy works for those chocolate shake people out there, or vanilla shake, or whatever you like. And that is, if I'm trying to drink a fluid through a straw, yeah, definitely missing out. If I'm trying to drink a fluid through a straw, let's start thinking about some factors that might be involved. Now, you go to the bar. You go, I want a margarita, and you give me the longest straw you got in this place. I want a straw that's 10 feet long. And you try to suck that margarita through a 10-foot long straw. How's that going to go for you? Real good? You're going to be sitting there with those pucker cheeks going, right? We could all kind of imagine this. We'd prefer no straw. But you got to have a straw in this analogy. So what do you now know about resistance and the length of a straw? As the length increases, what's going to happen to the resistance through that tube? Increase, decrease, no change. So is this going to be directly proportional or inversely proportional? Is the length of that tube going to be on top of the equation or on the bottom of the equation? As the length increases, resistance increases, so it's got to be on the top. You guys with me? Now, again, don't overthink these. It's actually 8 times the length. Don't worry about the 8. It's a constant. We're going to be able to get rid of it in just a minute. But this would be, in physics, it's AL is actually what is affecting the resistance. Now, the next thing to think about with our analogy, and shakes are a great one for this. Margaritas are too. Do you want a margarita that's like too frozen, where you have to sit there and wait 5 minutes for that crap to thaw out? Right? Try drinking a frozen material through a straw, and that's why shakes are so good. Right? You go to DQ, or yeah, right? DQ is the one where they put that thing up. What's a Blizzard? Where they put that upside down? Is that DQ? Right? They show you that it doesn't come out, and they don't give you a straw for that. They give you a spoon, right? Try to drink something like that through a straw. It's not going to go very well. True story? So the thicker the material, the thicker the material, the thicker the liquid. This is called viscosity. Viscosity is the thickness of a fluid. So something like molasses, honey, oil. These are very viscous fluids. They're very thick, and they're going to move through a tube slower. Does that make sense? Viscosity is defined by this crazy Greek letter right there. We're going to define these over on the right. 8 times the length equals length. This crazy nu equals viscosity, the thickness of that fluid. Is your blood viscous? Help me out, and then we can be done here. Hold on. Think of a protein shake. Let's think of a protein shake. Is a protein shake viscous? Anybody ever drank those protein shakes and it's like sludge? Right? Your blood has lots of proteins, lots of red blood cells in it. Is it just a fluid? No. There's a lot of material in your blood. So yes, it has viscosity. Is it as viscous as molasses? No, thank goodness. But is it way more viscous than water? Yeah. Does that make sense? Blood's actually pretty thick. The reason why it comes squirting out if you cut yourself is because of blood pressure. Blood pressure causes it to flow the way that it flows. You watch a lot of those movies. If you ever watch Dexter, for instance, right? Showtime, Dexter. There's so many liters of blood everywhere, and they make that blood look like it's water. Well, that's because it is. It's just dyed water in a lot of those movies. But blood's pretty darn viscous, and it clots really fast out in the open air. Length and viscosity. Two things to think about here is, does the length of your blood vessels change a lot in your body? Yes or no? Like in a 1 day period of time, are you going to be able to say, hey, blood vessels grow? No, you're not. So the length tends not to be a huge factor. Now, what if you're looking at a 7-foot person versus a 5-foot person? What's going to happen to the total length of blood vessels in that 7-foot person? Increase, decrease, no change. So what's going to start happening to the overall resistance inside of that 7-foot person's body? Increase, decrease, no change. And so what's going to happen is, if I have more resistance, the body's going to have to try to push harder using the heart to reach the blood flow demands of that body. So a 7-foot person is more likely to have heart failure than a 5-foot person because of all the resistance inside of their body. Does that make sense? Pretty crazy. One more thing to think about is adipose tissue. Although it doesn't require a ton of extravascularization, the more adipose tissue that a patient has, the more vascularization they have. All adipose tissue requires blood vessels. New adipocytes, or not new adipocytes because you don't get new adipocytes, but the bigger your adipocyte is, the more vascularization you have. So severe obesity, the length of the blood vessels goes up actually quite a bit, enough to actually cause a relatively large change in resistance, causing their heart to have to pump harder to reach the blood flow demands of that patient. It's one of the reasons why obese patients are more prone to heart failure than non-obese patients. The last variable is the most important variable. We're going to finish off with this variable. And it has to do with something about blood vessels we've already talked about quite a bit this semester. And that is the size of the tube. If I shrink-a-dink this size of this tube down, what's going to start happening to the blood pressure? What's going to start happening to the resistance inside of this tube? If I make it smaller, what's going to start happening? Oh, yeah. So I just said the size got smaller, but the resistance got greater. So is that going to be on the top of the equation or on the bottom of the equation? That's how we want to think about this. This has to do bottom, Tariq, right? Because it's inversely proportional. We said that as the diameter of the tube got smaller, decrease, the resistance got bigger. So you could just draw the arrows real quick like this, and you can see they're opposite. So it's got to be on the bottom. Is that clear to everybody? If they're opposite, it's bottom. If they're same, it's top. Now, in physics, we define the kind of diameter. It's not a complete diameter idea, but pi, 3.14, radius, lowercase r, to the 4th power. This pi, r to the 4th, has to do with the diameter of the tube. It's not the exact mathematical diameter, but it has to do with how tubes can change their size and stuff. So diameter, pi r to the 4th power. Sure, Tricia. Whether it's directly proportional versus inversely proportional has to do with if it changes. So let's look at this. If A equals B and B equals 1, what does A equal? And if B equals 2, what does A equal? So as B increased, what happened to A? Increase, decrease, no change. Now, if we start looking at C, so B's on the top of the equation here. So as B increased, A increased. But what if we did C? So if C equals, we're going to throw C into this mess. We'll just have, you know, the top of the equation is 1. If C equals 1, then A equals 1, because 1 over 1 would be 1. But what if C equaled 2 in this scenario? 1 over C, so A would equal 1 divided by 2. Nope, 1 divided by 2. If C equals 2, remember this says A equals 1 over C. So what just happened to A? As C got bigger, what happened to A? Did it increase or decrease? It decreased, right? So it's the same idea. You don't need to think outside of the box. If this is on the bottom of the equation, if this part of the equation increases, this part of the equation increases, since it's on the bottom of the equation, what's going to happen to the left side of the equation? Increase, decrease, no change. That's going to decrease. So let's think about this. Pi r to the 4th has to do with the diameter. So what did we just do to the diameter of the tube? We just made it bigger. And if I make a tube bigger in diameter, what happens to the potential blood flow through that tube? Increase, decrease, no change. It just increased. No, don't write decrease. Don't write decrease. I went straight to the end. Work with me. Work with me. The diameter just got bigger. So what just happened to the potential blood flow? Increase, decrease, no change. Good. Increase. Why did you guys go to decrease? Is because you're looking at this formula, but I'm getting there. So what is actually happening in this scenario is that diameter just got bigger. More blood can flow through there because there's less resistance along the walls of that tube. So as the diameter got bigger, the resistance just decreased. So let's go back on our formulas here and think about it step by step. Vasodilation occurs, the resistance drops. And as the resistance drops, resistance is inversely proportional to blood flow. So what happens to blood flow? It increases. Do you guys see how this equation links with this equation? Yes, no, maybe so? So that's exactly how a test question would come about, y'all. What I'll say is something like sympathetic nervous system fires. What do we know about the sympathetic nervous system in most blood vessels in the human body? If it has alpha 1 adrenergic receptors, alpha 1 means excitation. So the sympathetic nervous system fires and the alpha 1 adrenergic receptors are activated, then it's going to cause vasoconstriction. So what just happened to the resistance inside of that tube as I vasoconstricted? Increase, decrease, no change. And as the resistance increases, what's going to happen to blood flow through that tube? Increase, decrease, no change. Now you guys understand how, not just the thought process that this occurs, which we started weeks ago, but now you guys actually understand the physics behind it, which is pretty cool. Well, at least you've been taught the physics behind it, and it's going to take a couple of times to go through. Viscosity. Remember, this has to do with proteins in the blood or red blood cells in the blood. So what happens if somebody has like something like polycythemia, which means excessive red blood cell production? So somebody has polycythemia, what's going to happen to the viscosity of their blood if it starts to produce more erythrocytes? Increase, decrease, no change. And if the viscosity of that blood increases, what happens to the resistance of that blood? Increase, decrease, no change. And if the resistance increases, what happens to blood flow in that patient? Increase, decrease, no change. Oh, shit. Right? They have a disease that's causing less blood to flow out to the tissues of their body because they got a freaking protein shake going on in there. Does that make sense? What organ of the body makes over 90% of all your blood proteins? Always the bridesmaid, never the bride. So if you start getting liver failure, what might potentially happen to your protein production? Increase, decrease, no change. So what's going to start happening maybe just to your viscosity of your blood? If you have less proteins in your blood, less proteins. Remember, viscosity has to do with the thickness of that blood. So if you have less proteins, then it's less viscous. Does that make sense? So this is not necessarily a good thing in those liver failure patients because now all of a sudden the viscosity starts to drop. It becomes more water-like. So what's going to start happening to blood flow out to those tissues? Increase, decrease, no change. Good. Becca's got it. Don't be over, just don't, yeah, just listen to the questions I'm asking. Don't overthink the problem. This is more like water. So it runs through this tube a lot easier. So what's going to happen to blood flow out to the tissues in that patient? Increase, decrease, no change, y'all. Where most people are pausing are going, wait a minute, more blood flow, isn't that better? No, it's not better because the body needs Goldilocks. If blood flow is too high to a tissue, what's going to start happening to the fluid in that tissue? It's going to start to build up and it causes edema. And one of the first places that happens in a liver failure patient is in their nose. And that's why alcoholics get the red nose, is because of inflammation of tissue, breaking of blood vessels in that nose. And that's why Santa Claus is an alcoholic. I'll end my lecture there today. Ba-dum-bum. Cool. You guys now been introduced to the blood flow. We're going to be using intrinsic effects. How can we change blood flow? You probably are. Oop, I had a little glitch, but you probably already have a pretty good understanding of the primary way that we change blood flow in the human body. Oh, I'm not done. Shit. Do you see this power to the fourth? Do you guys see this guy right here? You guys know powers, right? If something has 1 to the 4th power, then that equals 1. But 2 to the 4th power, well, 2 times 2 times 2 times 2, that equals 16. So when I start throwing powers on things, a 2-fold change in the diameter would equal a 16-fold change in blood flow. You don't need to do that math, but is that pretty cool? I mean, is that a big number? It goes from 2 to 16? What that tells us is power. That means it's powerful. Power, get it? Powerful. So what's going to be more powerful? Something with a 4th power or something with no power whatsoever? Come on. What's going to be more powerful? Anything with a power, right? Does that make sense? So of the variables that you guys learned affect resistance, which one's the most powerful? Which one can the body make really small adjustments to and have a huge impact on blood flow? Let's go, let's go, let's go. We got this. Yeah. And how does the body determine the diameter of their blood vessels? What system controls the diameter of your blood vessels? Be more specific, Tariq, not just ANS. You're not wrong, but you're not fully correct. Sympathetic nervous system. We either activate the sympathetic or we inhibit the sympathetic, and we change the diameters of our tubes. And now we'll be done. So if I ask you guys a test question, what's the most powerful variable? The answer is diameter. And how does the body adjust this on the daily? Sympathetic nervous system. Okay? We'll talk more about this tomorrow. We'll talk more about how blood flow and blood pressure are two different things, but both are going to determine homeostasis. So tomorrow's all about blood pressure. So hopefully I'm driving your blood. No, I don't want to drive your blood pressure up. I hope I'm making this somewhat, doable. I know it's still hard and there's a lot of work. So keep reaching out to me with questions via text, and I will chat with you when you do. Thanks y'all for your patience, your time, your attention. A lot of work. I have faith in y'all.